Hello there and welcome to Life Beyond Seen, a place where curiosity is allowed to slow down, where questions are welcomed without urgency, and where science is invited to speak in a quieter voice. This is a space for wandering thoughts, late-night wondering, and ideas that don't demand answers right away. A place to listen, to drift, and to let the edges of the day soften a little. Tonight, we're turning our attention toward the ocean, not the friendly shoreline kind with postcards and sunburns, but the kind that reminds us how little of this planet truly belongs to us. There is a stretch of water off the eastern coast of Japan that has unsettled sailors, confused scientists, and quietly resisted explanation for decades. It does not announce itself with towering cliffs or dramatic borders. On most maps, it looks ordinary, blue, calm, unremarkable. And yet, for generations, it has carried a name that feels heavy when spoken aloud. The Devil's Sea. A name that sounds more like a warning than a location. A place where ships have vanished, instruments have failed, and confidence has a habit of dissolving the farther you travel into it. What makes this region unsettling is not a single disaster or one dramatic event. It's the pattern. The way stories repeat themselves across years and across witnesses who never spoke to one another. The way modern explanations arrive, pause for a moment, and then quietly admit they are incomplete. Scientists don't like mystery without boundaries. They prefer variables, probabilities, margins of error. But this part of the Pacific has a tendency to ignore neat categories. It doesn't behave consistently. It doesn't always announce danger. Sometimes, it simply removes things from the surface and leaves behind questions that don't settle easily. You don't have to believe in anything supernatural to feel uneasy about that. Before we move any deeper into these waters, take a moment to notice where you are right now. Are you listening late at night, when the world feels thinner and quieter, or earlier in the day, when thoughts still have some distance to travel? Where are you, and what time is it there? It's a small detail, but fitting, considering that this story crosses time zones, generations, and long gaps where nothing was recorded at all. Different people, different moments, all brushing up against the same patch of sea and coming away with the same unsettled feeling. If you find this kind of exploration calming, or if it helps you unwind and let your thoughts slow down, you're very welcome to like the video or subscribe to the channel. It helps this quiet corner reach others who might be looking for the same thing. No rush, no pressure, just a small gesture if it feels right. Now, imagine standing on the deck of a ship as the coastline fades behind you. The land doesn't disappear suddenly, it thins out. Mountains soften into shapes, buildings shrink into suggestions, and eventually there's nothing but water in every direction. The ocean has a way of doing that, of erasing reference points until all you have left is motion and sound. The steady rhythm of waves, the low mechanical hum beneath your feet, the horizon stretching so evenly that it almost looks artificial. This is where confidence usually lives. In routines, in charts, in instruments that tell you where you are and how fast you're moving. Sailors trust these things because they have to. The ocean doesn't offer second opinions, and yet, in the Devil's Sea, that trust has been broken more than once. Compasses that refuse to behave, readings that contradict one another, signals that fade without explanation. Not dramatically, not with alarms blaring, just quietly enough to make you doubt your own senses. For centuries, long before the name Devil's Sea ever appeared in print, local fishermen knew there were places where you didn't linger. The warnings weren't shouted. They didn't need to be. They were passed along in the practical language of people who rely on the sea, but don't romanticize it. Certain routes were avoided. Certain waters were crossed quickly without stopping. Nets were cast elsewhere. Questions weren't always asked, because answers weren't guaranteed, and the cost of curiosity could be high. This wasn't fear in the theatrical sense, it was familiarity, the kind that comes from watching others not return. When Western scientists later encountered reports from this region, many assumed exaggeration. Oceans are dangerous everywhere, after all. Ships sink, storms happen, human error fills in the gaps, and in many cases that reasoning holds up. But here, the explanations kept fraying at the edges. Weather reports didn't always match outcomes, wreckage didn't always surface, patterns appeared where randomness should have dominated. What unsettled researchers most wasn't that strange things happened, but that they happened without leaving enough behind to study. Science advances through evidence, through remnants, through measurable after effects. The Devil's Sea has a reputation for removing those. Even today, with satellites circling overhead and sensors mapping the ocean floor, there are areas where data thins out. Not because we aren't looking, but because the environment itself is unstable. The seabed shifts. Volcanic activity reshapes the terrain without notice. Chemical processes occur beneath the surface, invisible and indifferent to human schedules. The ocean here is not a static backdrop. It is active, restless, and sometimes violent in ways that don't announce themselves ahead of time. It's tempting to jump ahead, to reach for explanations quickly, to list causes and move on, but doing so misses something important. The unease surrounding the Devil's Sea isn't just about danger, it's about unpredictability, about the uncomfortable reminder that even now there are parts of this planet that don't operate on our terms, places where knowledge remains provisional and confidence has to remain flexible. This is not a story about monsters rising from the deep, or ships swallowed whole in a single dramatic moment. It's quieter than that, more procedural, more frustrating. It's about missing vessels that leave behind paperwork but no remains, about research missions that return with more questions than answers, about scientists who do their work carefully and still admit, sometimes reluctantly, that there are limits to what can be confirmed. As we continue, we'll move slowly. We'll look at where this region sits, how it compares to other infamous stretches of ocean, and why comparisons only go so far. We'll talk about ships that vanished, not as legends, but as documented absences. We'll listen to the voices of people who work these waters long before modern instruments arrived, and we'll examine what happens when even advanced technology starts to struggle. For now, let the image settle. A calm surface, an unremarkable horizon. No visible warning signs, just water behaving like water until it doesn't. Somewhere ahead, the ocean begins to act differently, not all at once, but enough to leave an impression that lingers long after the shoreline has disappeared. For a long time, the water east of Japan did not have a dramatic reputation written onto maps or carved into official warnings. It appeared, at least on the surface, like any other part of the Western Pacific Ocean. Blue on charts, predictable routes, familiar currents. Ships passed through it every year without incident, carrying cargo, people and quiet routines from one port to another. Nothing about it announced danger in the way jagged coastlines or icy seas tend to do. There were no towering cliffs or obvious natural barriers, just open water stretching outward in a way that felt manageable, navigable, and most of the time calm. And yet, among those who work the sea closely, this area carried a different weight. The unease did not begin with dramatic disappearances or international headlines. It began with hesitation, with small choices made quietly, fishermen altering their routes without offering explanations, captains choosing longer paths even when fuel was precious and schedules were tight, warnings shared casually, almost dismissively, as if drawing too much attention to them might invite trouble rather than prevent it. The tone was never panicked, it was practical. Certain waters were simply not places where you lingered. Over time, this stretch of ocean came to be known as the Devil's Sea, or sometimes the Dragon's Triangle, a name that sounds theatrical but grew out of something much more restrained. The name did not originate as a claim of the supernatural. It was a label for discomfort, a way to describe a place where normal expectations stopped lining up reliably with outcomes, where confidence in navigation quietly eroded the farther you moved into it. Geographically, the Devil's Sea lies off the eastern coast of Japan, roughly south of Tokyo and extending toward the Ogasawara Islands. It sits in a region where tectonic plates meet, where the ocean floor is fractured and restless. On paper, this should not be surprising. Japan itself exists because of geological tension. Earthquakes, volcanoes, and deep ocean trenches are familiar parts of the landscape. The sea reflects that instability, even if its surface often hides it well. What unsettled early observers was not that the ocean was dangerous. All oceans are. What troubled them was inconsistency. Storms did not always precede trouble. Equipment failures occurred without obvious causes. Ships disappeared without leaving behind debris fields that could be studied or explained. Sometimes there were witnesses. Sometimes there were none. What remained were gaps in records, and a growing sense that this particular area did not behave like its neighbours. Sailors are not easily shaken by strange stories. Their work depends on skepticism. Superstition exists, of course, but it tends to coexist with a strong reliance on experience. The sea teaches patterns quickly, and those who survive long enough learn which warnings matter and which do not. In the case of the Devil's Sea, the warnings endured because they aligned with lived experience. They did not contradict it. Long before modern navigation systems, people in coastal communities passed down knowledge through observation rather than theory. They watched currents, they noted weather shifts, they remembered which voyages ended quietly and which did not end at all. Over generations, certain conclusions solidified. This was a place where the sea could change its behaviour quickly, where calm conditions could give way to chaos without the usual signals, where returning was less guaranteed than elsewhere. These were not stories told for entertainment. They were practical notes embedded in culture. A fisherman does not need to understand the chemical composition of water to know where nets come back empty, or where boats return damaged, or where names stop being spoken because there is nothing left to say about them. Over time, these observations accumulated into something resembling a reputation, though it was not written down formally. When outside researchers later began to examine the region, they brought with them a different framework: satellite imagery, oceanographic surveys, statistical models. The assumption was that with enough data, the mystery would resolve itself, and to some extent it did. Certain risks became clearer. The area is dotted with undersea volcanoes, many of them active. The seabed is uneven and unstable. Sudden changes in water temperature and chemistry are possible. None of this is unusual in tectonically active regions. But even with these explanations, something did not quite settle. Volcanic activity can account for sudden disturbances, but not always for the absence of wreckage. Rough seas can sink ships, but they usually leave something behind. Magnetic anomalies can interfere with instruments, but they rarely do so consistently across different systems without affecting others in measurable ways. Each explanation worked in isolation. Together, they left gaps. Part of the problem lies in how humans expect danger to behave. We look for warning signs, patterns that repeat predictably, conditions that escalate before they collapse. The Devil's Sea often fails to provide these comforts. Its hazards do not always announce themselves. They emerge from below, from chemical processes or geological shifts that are invisible at the surface. To someone standing on a deck, the ocean may look no different than it did an hour earlier. This unpredictability creates a specific kind of fear, not the sharp fear of an approaching storm, but the quieter fear of uncertainty, the kind that makes you double-check readings that should not need checking, the kind that makes experienced professionals uneasy without being able to explain why in clear terms. It is difficult to communicate this discomfort to those who have not felt it. Words tend to exaggerate or understate it. Most sailors choose understatement. As reports accumulated, comparisons inevitably emerged. The Devil's Sea was likened to the Bermuda Triangle, another region where disappearances, instrument failures, and unresolved incidents captured public imagination. The comparison made sense at a distance. Both were oceanic regions associated with loss. Both attracted a mix of scientific inquiry and speculative storytelling. Both became shorthand for places where the sea appeared to misbehave, but those who studied the Devil's Sea closely were cautious about the comparison. The environmental conditions are different. The geological context is different. The cultural history surrounding each region developed independently. While the Bermuda Triangle sits within a heavily trafficked and well-studied part of the Atlantic, the Devil's Sea occupies a region where geological volatility plays a more active role. Treating them as equivalents risked oversimplifying what made this place distinct. Another complicating factor was silence. Many incidents in the Devil's Sea did not generate international attention when they occurred. Records were sometimes sparse. Political priorities shifted. In some cases, acknowledging losses publicly raised uncomfortable questions about safety, oversight, or preparedness. It was easier at times to allow events to fade quietly rather than frame them as part of a larger pattern. This quiet accumulation of unresolved incidents contributed to the region's unsettling reputation more than any single catastrophe. There was no defining moment that announced the Devil's Sea to the world. Instead, there was a gradual realization among those paying attention that something about this area resisted closure. Investigations ended without conclusions, reports closed with cautious language, files were archived without resolution. Scientists are trained to tolerate uncertainty, but only up to a point. Uncertainty is meant to shrink as knowledge expands. In the Devil's Sea, it often persisted. New tools revealed more complexity rather than clarity. Better measurements uncovered additional variables. Each layer of understanding exposed further instability beneath it. This does not mean the region is inexplicable. It means it is demanding. It requires an acceptance that some environments operate on timescales and mechanisms that are difficult to observe directly. Undersea volcanic activity, for example, can release gases that alter water density without leaving obvious surface signs. These changes can affect buoyancy suddenly and locally. A vessel passing through such an area might experience forces that are difficult to anticipate or counter. Magnetic irregularities linked to the geology of the seabed can interfere with navigation systems in subtle ways. Not dramatic failures, but enough to introduce error, enough to compound other problems. When combined with rough seas or mechanical issues, small discrepancies can become significant quickly. The unsettling nature of the Devil's Sea lies in this layering of risks. No single factor is extraordinary on its own. Together they create an environment where margins for error narrow rapidly, where recovery from small problems becomes more difficult, where the sea does not need to be violent to be dangerous. Despite advances in technology, modern vessels still rely on assumptions about stability and predictability. The ocean usually rewards those assumptions. In this region, it sometimes challenges them. That challenge is not constant. Many ships pass through without incident. That too contributes to the unease. The danger is not reliable enough to be avoided entirely, nor rare enough to be dismissed. For scientists, this presents a difficult question. How do you study a problem that does not behave consistently? How do you gather data from events that leave little physical evidence? How do you separate coincidence from pattern when records are incomplete and variables are numerous? These questions do not have simple answers, and that is precisely what keeps the Devil's Sea from settling comfortably into any single explanation. It remains a place where confidence must be provisional, where conclusions are offered carefully, where phrases like likely and suggests appear more often than definitive statements. The reputation of this quiet stretch of water did not grow out of imagination alone. It grew out of experience, repeated enough times to leave an impression that refused to fade. It is a reputation built not on spectacle, but on absence, on ships that did not return, on data that did not align, on a sense that the ocean here operates according to rules that are still being mapped. As attention gradually shifted toward understanding how and why this region behaves the way it does, researchers began to look deeper, not just at the surface, but beneath it. The unsettling reputation of the Devil's Sea became less about legend and more about geology, physics and environmental instability. The questions did not disappear. They changed shape. And it is in that shift from whispered warnings to formal inquiry that the story continues to unfold, moving from reputation into investigation, from unease into cautious examination, as scientists began to ask not whether this stretch of water was dangerous, but what exactly made it so difficult to predict. When the comparison began to circulate, it did not come from tabloids or late-night radio hosts. It emerged gradually, almost reluctantly, from scientists, journalists and maritime officials who noticed that certain descriptions kept sounding familiar. Ships disappearing without clear wreckage, instruments behaving oddly, official reports closing without firm conclusions. The pattern echoed something already lodged in the public imagination. And so, eventually, someone said it out loud. This region off Japan's coast was being described more and more often as Japan's answer to the Bermuda Triangle. At first glance, the comparison feels inevitable. The Bermuda Triangle had already become shorthand for a particular kind of unease, a place where modern confidence seemed to falter. By the time the Devil's Sea entered wider discussion, the idea of a mysterious oceanic zone was already familiar to global audiences. Attaching the comparison helped people orient themselves. It gave journalists a hook. It gave readers a reference point. It gave scientists something to argue against or refine. But comparisons, while useful, can also flatten important differences. The Bermuda Triangle occupies a vast area of the Western Atlantic, loosely defined by points near Florida, Bermuda and Puerto Rico. It sits along major shipping and flight routes and has been intensely trafficked for centuries. Its mythology grew alongside the rise of mass media, aviation and global trade. The Devil's Sea, by contrast, developed its reputation more quietly, within a regional maritime culture that did not broadcast its anxieties outward. The similarities are real, but so are the divergences. What links the two regions most strongly is not mystery itself, but uncertainty that persists even after investigation. In both cases, skeptics have correctly pointed out that many incidents attributed to strangeness can be explained by weather, human error, or misreporting. This is true, but it is also incomplete, because alongside the explainable events sit others that resist neat categorization, not because they are supernatural, but because the available data is thin, contradictory, or missing altogether. In Japan, this comparison carried particular weight. The country has a long and complex relationship with the sea. As an island nation, maritime routes have always been essential. Fishing, trade, exploration and defence are all deeply intertwined with ocean navigation. There is also a strong cultural respect for natural forces, shaped by centuries of earthquakes, tsunamis, and volcanic eruptions. The idea that a specific stretch of ocean might demand special caution did not feel absurd. It felt plausible. When international observers labelled the Devil's Sea as Japan's Bermuda Triangle, Japanese scientists were careful in their responses. Some rejected the framing outright, concerned that it invited sensationalism. Others acknowledged the parallels but emphasised environmental differences. A few saw value in the comparison as a way to attract research funding and global attention to an understudied region. The debate itself revealed something important. The discomfort was not about the label, it was about what the label implied. Calling a place a triangle of mystery suggests boundaries. It suggests containment. The Devil's Sea does not offer that clarity. Its edges are not fixed. Reports vary about its precise location and extent. Some place it closer to the Izu Islands, others extend it toward the Bonin Trench. This ambiguity complicates study. Scientists prefer defined systems. The ocean does not always cooperate. Another important distinction lies beneath the surface, quite literally. The Devil's Sea sits atop a highly active geological zone where several tectonic plates interact. Submarine volcanoes dot the seabed, some mapped, others still uncertain. These volcanoes can erupt without warning, releasing heat, gas, and debris into the surrounding water. Such activity can alter water density and chemistry rapidly and locally, creating conditions that affect buoyancy and stability. The Bermuda Triangle does not share this level of volcanic activity. Its hazards are more closely tied to weather systems, currents, and heavy traffic. The Gulf Stream, for example, can carry wreckage far from its origin, complicating search efforts. This has often been cited to explain why debris is not always found. In the Devil's Sea, debris may never reach the surface at all. Despite these differences, the human response to both regions follows a familiar pattern: initial skepticism, careful investigation, public fascination. Then a kind of uneasy truce where explanations exist but do not fully close the case. Scientists do not declare defeat, but they also do not claim mastery. The ocean retains a degree of autonomy. Media coverage played a significant role in cementing the comparison. As Japanese incidents were reported internationally, editors reached for language that audiences would recognize. Japan's Bermuda Triangle was memorable. It suggested danger without requiring detailed explanation. Over time, repetition gave it staying power. The phrase appeared in documentaries, articles, and later online discussions, reinforcing the association. This created a feedback loop. Public interest increased. Researchers faced more questions. Funding proposals referenced the comparison. At the same time, the pressure to distance serious science from sensational narratives grew. No one wanted the region reduced to folklore alone. The challenge was to communicate risk without exaggeration, uncertainty without mysticism. From a scientific standpoint, comparing the two regions has both advantages and drawbacks. On the positive side, it encourages comparative analysis. Researchers can ask whether similar mechanisms might be at work. Are there shared patterns in magnetic anomalies? Do both regions experience unusual wave behavior? How does traffic density influence reporting? These questions are productive. On the negative side, the comparison can bias interpretation. Once a region is framed as mysterious, normal accidents may be interpreted through that lens. Coincidence can begin to look like pattern. Scientists are acutely aware of this risk. Confirmation bias is not limited to the public. It can shape research agendas if left unchecked. Japanese oceanographers have often emphasized that the Devil's Sea does not require supernatural explanations. The danger lies in natural processes that are poorly understood and difficult to monitor in real time. The problem is not that science has failed, but that the environment is complex and dynamic. The ocean floor here is not stable. It is actively reshaping itself on timescales that do not align neatly with human observation. One of the more unsettling aspects of the comparison is how both regions challenge the assumption that technological progress guarantees safety. Modern ships are equipped with advanced navigation systems, satellite communication, and real-time weather data, yet incidents continue to occur. This does not mean technology is ineffective. It means it operates within limits. In the Devil's Sea, those limits are tested by factors that are not always visible. Gas releases from the seabed can create zones where water behaves differently. Magnetic disturbances can introduce subtle errors. Sudden wave formation can overwhelm vessels before evasive action is possible. Each of these factors alone might be manageable. Together they reduce reaction time. This convergence of risks mirrors some of the challenges faced in the Bermuda Triangle, where rapidly changing weather and heavy traffic increase the likelihood of compounding errors. In both cases, the ocean does not need to act dramatically to be dangerous. Small deviations can escalate quickly. Culturally, the comparison also reveals how societies process uncertainty. The Bermuda Triangle became a canvas for speculation, partly because it sat at the intersection of Cold War anxieties, technological optimism, and expanding media reach. The Devil's Sea emerged within a different context, shaped by regional maritime traditions and a more reserved public discourse. Yet both tapped into a shared human discomfort with environments that resist control. It is worth noting that many Japanese researchers prefer to avoid the comparison altogether. They argue that it obscures more than it clarifies. The Devil's Sea is not a riddle to be solved once and forgotten. It is an active system that requires ongoing monitoring. Treating it as a counterpart to a popular mystery risks diverting attention from practical safety concerns. And yet, the comparison persists because it captures something real. Not magic, not curses, but the feeling that there are places where our models lag behind reality, where explanations trail events rather than anticipate them, where confidence must be provisional. As research continued, scientists began to move beyond surface comparisons and into deeper investigation. Instead of asking whether the Devil's Sea was mysterious in the same way as the Bermuda Triangle, they began asking what specific processes operated here and how they interacted. The focus shifted from labels to mechanisms, from reputation to measurement. This shift did not erase the comparison, it contextualized it. The Devil's Sea became less a counterpart and more a case study, a reminder that different oceans pose different challenges, and that mystery is not a category but a condition, one that persists when systems are complex and observation is incomplete. In the process of disentangling myth from mechanism, researchers found themselves confronting a more uncomfortable truth. Even with careful study, some environments remain difficult to predict, not because we lack intelligence or effort, but because nature does not simplify itself for our convenience. The Devil's Sea earned its comparison not because it mirrors the Bermuda Triangle perfectly, but because it exposes the same vulnerability. Our reliance on patterns, our expectation of consistency, our discomfort when those expectations fail, and as attention continued to focus on this region, the next questions became unavoidable. What exactly had been lost here, and under what circumstances, when speculation gave way to documented absence, and the record itself began to thin? Long before scientists began running models or governments commissioned reports, the reputation of the Devil's Sea was shaped by something far more concrete than theory. Ships left port and did not return. Not dramatically, not always during storms, and not with enough consistency to trigger immediate alarm, but often enough to leave a residue of unease in maritime records. These were not legends invented after the fact. They were absences logged in shipping manifests, insurance documents, and port registries, each one small on its own but collectively difficult to ignore. Maritime history is full of loss. The ocean has claimed vessels since humans first trusted wood and sail to carry them beyond sight of land. Storms capsize ships. Mechanical failures strand crews. Navigation errors send hulls onto reefs or into shallows, where they break apart slowly. Most of these events leave behind evidence. Debris washes ashore. Lifeboats are found. Distress signals are logged. Survivors tell their stories. Even when tragedy strikes, there is usually something left to examine. In the Devil's Sea, that expectation was not always met. One of the earliest patterns that drew attention was not the scale of the losses, but their quietness. Ships would depart, often on routine voyages, and simply fail to arrive. Search efforts would be mounted, nearby routes would be checked, weather records reviewed, and then, with little else to go on, the file would close. No wreckage. No confirmed sightings, no clear cause, just a vessel listed as missing, its fate unconfirmed. For shipping companies and families alike, this lack of closure was deeply unsettling. The ocean is dangerous, but it is also predictable in its unpredictability. When something goes wrong, there is usually a chain of events that can be reconstructed. In these cases, the chain appeared to break mid-air. The Devil's Sea lies within a busy maritime region. Routes connecting mainland Japan to outlying islands and international destinations pass through or near it. Fishing vessels operate there seasonally. Research ships have crossed it repeatedly. This was not an isolated or rarely travelled patch of water. That made the disappearances harder to dismiss as anomalies. One frequently cited incident involved small fishing boats rather than large commercial ships. These vessels were more vulnerable, easier to lose, and less likely to carry advanced communication equipment, especially in earlier decades. Some never sent distress calls, others reported trouble briefly and then went silent. When wreckage failed to surface, explanations range from sudden weather changes to mechanical failure. Yet similar boats operating in nearby waters did not experience the same rate of unexplained loss. As time went on, attention shifted from individual cases to patterns. Certain routes appeared riskier than others. Certain seasons showed higher incidents. Certain types of vessels vanished more often. None of these correlations were strong enough to stand alone as definitive explanations, but together they suggested that the environment itself played an active role. One of the most troubling episodes came in the early 1950s, when a Japanese government-sponsored research vessel was sent into the region to investigate reports of unusual activity. This was not a fishing boat or a cargo ship. It was a ship equipped specifically to study the sea, staffed by trained personnel and operating with official oversight. Its mission was to gather data, not to test folklore. The vessel did not return. The loss of a research ship changed the tone of the conversation almost immediately. Disappearances of fishing boats could be attributed, at least in part, to limited equipment or exposure to harsh conditions. The loss of a state-backed research vessel raised different questions. It suggested that even careful planning and professional operation did not guarantee safety. Details surrounding the incident were sparse. Records indicated that the ship encountered difficulties and then vanished. No confirmed wreckage was recovered. No survivors were found. The investigation that followed acknowledged environmental hazards but stopped short of providing a definitive cause. For scientists, this was deeply unsettling. The tools designed to bring clarity had themselves been swallowed by uncertainty. This incident marked a turning point. Official interest in the Devil's Sea intensified. At the same time, public discussion became more cautious. Authorities were reluctant to amplify fear, but they could not ignore the implications. A region capable of claiming a research vessel without leaving behind clear evidence demanded respect. Insurance companies took note as well. Maritime insurers are not sentimental institutions. They assess risk based on data. Over time, certain routes near the Devil's Sea were quietly flagged as higher risk. Premiums adjusted, policies changed. These shifts rarely make headlines, but they speak volumes. When financial models incorporate caution, it reflects patterns recognized over years, not anecdotes. One challenge in assessing ship disappearances lies in reporting itself. Not all losses are documented equally. Smaller vessels may not be tracked rigorously. Records from earlier decades can be incomplete or lost. Political and economic pressures can influence how incidents are described. A ship listed as lost due to weather may, in reality, have encountered a combination of factors that were poorly understood at the time. This complicates retrospective analysis. Scientists attempting to reconstruct patterns must rely on imperfect data. Gaps in records create uncertainty. In the Devil's Sea, those gaps are particularly wide. Another complicating factor is the seafloor itself. The region sits above deep trenches and volcanic structures that can pull wreckage downward quickly. In areas with steep underwater topography, debris may not drift widely. It may sink almost vertically, settling in locations that are difficult to access or survey. Even modern sonar struggles in such environments. Submarine volcanic activity adds another layer of complexity. Eruptions can produce sudden disturbances, including shock waves and rapid changes in water temperature and density. These events may not always break the surface or register clearly on distant monitoring equipment. A ship passing overhead might encounter forces that compromise its stability without warning. In some cases, scientists have proposed that large releases of volcanic gases, such as methane or carbon dioxide, could reduce water density enough to affect buoyancy. In theory, this could cause a vessel to lose lift suddenly, leading to rapid sinking. While this mechanism remains debated, it is taken seriously enough to be studied. What makes it unsettling is that it leaves little behind. A ship could sink quickly without breaking apart, leaving minimal debris. Magnetic anomalies present another challenge. Certain regions of the ocean exhibit irregular magnetic fields due to the composition of the seabed. In the Devil's Sea, these anomalies may interfere with compasses and navigation instruments. Small errors in heading can accumulate over time, particularly in poor visibility or rough conditions. A ship slightly off course may encounter hazards it was not prepared to face. None of these explanations are exotic. They are grounded in physics and geology. And yet, when combined, they create scenarios that are difficult to predict and harder to document. This is what distinguishes the disappearances associated with the Devil's Sea from more familiar maritime accidents. The mechanisms involved do not always leave clear fingerprints. Families of lost crews often faced years of uncertainty. Without wreckage or confirmed accounts, official death declarations could be delayed. Insurance claims stalled. Mourning became suspended. This human cost rarely features prominently in scientific discussions, but it underscores why unresolved disappearances matter. They're not abstract puzzles, they are lived absences. As decades passed, the rate of unexplained losses appeared to decline. Improved technology played a role. Better weather forecasting, satellite tracking, and communication systems reduced vulnerability. Ships became more robust. Routes adjusted. This led some observers to conclude that the danger had been overstated, that the Devil's Sea was a relic of earlier, less informed times. But researchers caution against that conclusion. A reduction in incidents does not necessarily indicate that the underlying hazards have disappeared. It may simply reflect improved avoidance. Mariners now know where to be cautious. Certain areas are monitored more closely. Research missions are planned with greater awareness of risk. The question then becomes not whether ships still vanish, but what those earlier losses reveal about the environment. Each missing vessel represents a data point that cannot be fully recovered. Together, they form an incomplete but troubling picture of a region where multiple risk factors converge. Comparisons with other parts of the Pacific Ocean highlight this convergence. There are many tectonically active zones. There are many regions with heavy traffic. There are many places prone to sudden weather changes. Few combine all of these elements in the same way, over the same area, with the same history of unresolved loss. Scientists studying these disappearances emphasize caution in interpretation. Correlation does not imply causation. Some losses attributed to the Devil's Sea may have occurred nearby rather than within its core. Others may have been misreported. Yet even after accounting for these factors, a residue remains. A number of cases resist confident explanation. That residue is what keeps the subject alive. It is what drives continued interest, not from those seeking mystery for its own sake, but from those trying to understand how complex systems fail. The ocean is a system, ships are systems. When multiple systems interact under stress, unexpected outcomes emerge. In the Devil's Sea, those outcomes sometimes included silence. As investigations continued, focus began to shift away from individual incidents and toward underlying structures. Researchers started asking broader questions. What lies beneath this water? How active is the seabed, really? What processes occur there that we cannot easily observe? These questions pointed downward, toward the ocean floor, where answers might be hidden beneath layers of sediment and stone. Understanding why ships did not come back required understanding what they were passing over, and that meant turning attention away from the surface, toward a landscape shaped by fire, pressure, and constant movement. A landscape that had been quietly influencing events above it all along. Long before official investigations, before reports were filed and terminology hardened into scientific language, the knowledge of this region lived almost entirely with the people who worked it daily. Not researchers, not naval officers, not journalists, but fishermen. Men who learned the sea through repetition, through exhaustion, through small corrections made instinctively rather than calculated. Their relationship with the water, was not theoretical. It was transactional. You went out, you came back, or you didn't. And over time, patterns emerged that never needed to be written down to be understood. Fishing communities along the eastern coast of Japan have always treated the ocean with a particular kind of respect. Not fear exactly, and certainly not romance, but an understanding that the sea does not reward confidence for its own sake. You listen to it. You watch it. You remember what it did the last time you ignored a small sign. This mindset shaped how warnings about the Devil's Sea were shared. They were not delivered as stories meant to entertain. They were offered as advice meant to be followed. In these communities, no one stood on a dock to give speeches about cursed waters. Instead, a younger fisherman would notice that certain elders adjusted their routes slightly, even when it cost them time or fuel. They would see nets cast elsewhere, despite reports of good catches farther out. When asked why, the answers were rarely elaborate. The water there behaves strangely. The sea feels wrong today. We don't stay there long. Simple statements, offered without drama. This kind of language frustrates outsiders. It sounds vague, unscientific, impossible to verify. But it reflects a form of knowledge built through long exposure rather than measurement. Fishermen notice changes others miss. Subtle shifts in wave rhythm, differences in how the boat responds beneath their feet, variations in colour, smell or sound that do not register on instruments, but signal that something is different. Over generations, these observations coalesced into informal boundaries, places you crossed quickly, places you avoided entirely if conditions were not ideal, places you did not fish at night. These boundaries were flexible, not fixed lines on a map. They changed with season, weather and experience, but the core warning remained consistent. This was not a forgiving stretch of water. Folklore grew alongside this practical knowledge, but it did not replace it. Stories about sea dragons, spirits or demons were never meant to serve as literal explanations. They were metaphors, ways of encoding caution into memory. A story about a creature that drags boats under without warning communicates something useful. It tells you that danger can arrive suddenly and from below. It tells you that calm surfaces are not guarantees of safety. In Japanese maritime tradition, folklore often functions this way. It does not deny natural causes. It supplements them. Spirits and monsters personify forces that are otherwise invisible or poorly understood. Long before tectonic plates or methane hydrates were part of the vocabulary, people still needed a way to talk about places where the sea behaved unpredictably. Myth provided that language. Importantly, these stories were not told indiscriminately. They were contextual. A child might hear them as bedtime tales. A teenager might hear them as half-joking warnings. A working fisherman heard them as reminders, reinforced by experience. The tone shifted depending on who was listening. What remained constant was the underlying message. Pay attention. Don't linger. Respect this place. Western observers who later encountered these stories sometimes misunderstood them. Accounts of dragons and demons were interpreted as superstition, evidence that fear rather than observation guided behaviour. This reading missed the point. The stories were not the source of caution. They were the packaging. The caution itself came from lived outcomes. There are recorded instances of fishermen returning early from otherwise promising trips because the water began behaving strangely. Engines sounded different. The boat felt unstable. Instruments showed minor inconsistencies, nothing dramatic enough to justify panic, enough to justify leaving. In many cases, those decisions were later validated by reports of sudden storms or disturbances in the same area. These decisions rarely appear in official records. They are invisible in accident statistics because nothing happened. A boat that turns back safely does not become data. This creates a skewed picture. Scientific analysis often focuses on failures because they are measurable. The countless avoided incidents guided by intuition and experience remain uncounted. Warnings passed at sea also travelled laterally, not just vertically through generations. Crews shared information with one another quietly. A nod, a short conversation at port, a comment about conditions farther out. No one needed to explain the Devil's Sea in detail. Mentioning it was enough. Everyone knew what that meant. Interestingly, these warnings did not always align with official advisories. Government-issued navigation warnings tend to focus on weather, traffic, and known hazards. They are necessarily conservative and standardized. Fishermen operate in a different informational ecosystem. They integrate official data with immediate sensory feedback and communal memory. When the two conflicted, lived experience often took precedence. This gap between official knowledge and informal warning systems created tension at times. Authorities were reluctant to acknowledge danger that could not be quantified easily. Acknowledging it raised questions about responsibility and regulation. Fishermen, meanwhile, had little incentive to formalize their warnings. Doing so might invite scrutiny or restrictions that interfered with their livelihoods. As a result, much of what was known about the Devil's Sea remained unofficial. It existed in habits rather than documents, in routes adjusted slightly rather than lines redrawn, in glances exchanged rather than reports filed. When scientific expeditions began to take a closer interest in the region, some researchers sought out local knowledge. They interviewed fishermen, reviewed oral histories, and compared accounts. What they found was not a single coherent narrative, but a consistency of concern. Different people described different incidents, but the emotional tone was similar: caution, unease, respect. One recurring theme in these accounts was unpredictability. Fishermen described days when the sea appeared normal until it didn't. Calm conditions disrupted without clear warning. Sudden changes in current direction. Waves behaving inconsistently, crossing rather than aligning. Boats responding sluggishly to steering inputs. These descriptions align uncomfortably well with later scientific theories about undersea activity and gas release. Another theme was silence. Engines cutting out without clear cause, radios crackling or losing signal briefly. Not complete failure, but interruption. Enough to unsettle. Enough to suggest that something external was interfering, even if no one could say what. Folklore absorbed these experiences and returned them as stories that emphasized humility. Tales where arrogance led to loss, where ignoring warnings invited disaster, where survival depended on listening rather than conquering. These narratives reinforced practical behavior. They reminded listeners that the sea did not respond to bravado. Over time, as fewer people made their living directly from fishing, and more relied on technology, some of this informal knowledge began to fade. Younger generations spent less time at sea. Routes became automated. Trust shifted from intuition to instruments. This transition brought many benefits. It also introduced new vulnerabilities. Technology excels at consistency. It struggles with environments that behave inconsistently. Fishermen accustomed to reading subtle cues were often the first to notice when instruments failed to capture emerging danger. Their warnings, however, carried less weight in a system that prioritized standardized data. This does not mean folklore replaced science or that intuition is superior to measurement. It means that in complex environments, different forms of knowledge capture different aspects of reality. The Devil's Sea exposed the limits of any single approach. As scientists began to re-examine the region with this in mind, they started paying closer attention to accounts that had previously been dismissed. Patterns described informally by fishermen were compared with geological surveys and satellite data. In some cases, correlations emerged. Areas avoided traditionally aligned with zones of known volcanic activity or magnetic disturbance. This did not retroactively validate every story, nor did it transform folklore into data. It did something more subtle. It suggested that long-term exposure, even without formal measurement, can detect instability before it becomes catastrophic. It suggested that warnings passed quietly at sea were not merely cultural artifacts. but adaptive responses to an environment that punished complacency. The Devil's Sea, in this light, was never simply a mystery imposed on unsuspecting sailors. It was a place that communicated its volatility repeatedly, in ways that were easier to feel than to quantify. Those who listened adjusted. Those who didn't sometimes vanished. As modern research continued, the gap between folklore and science narrowed slightly. Not because stories were proven true in a literal sense, but because the conditions they pointed toward became more clearly defined. Submarine volcanoes, shifting seabeds, chemical processes altering water behaviour. None of these require demons or dragons to be dangerous. And yet, the language of folklore persists, not because it explains the mechanisms, but because it captures the experience, the sense that the sea here is alert, reactive, and unwilling to be taken for granted. That sense does not disappear when equations are written. It remains, especially among those who have felt it directly. Warnings passed at sea are rarely dramatic, they're economical. A pause before answering a question. Suggestion to wait another day. A route adjusted without comment. These are not the gestures of fear. They are the gestures of people who have learned, sometimes painfully, that survival depends on recognizing when a place demands extra caution. As attention continued to turn toward formal investigation and state-sponsored research, this informal layer of knowledge remained present, influencing decisions quietly. Even as instruments improved and explanations multiplied, there were still moments when the oldest advice proved most relevant. Don't linger. Pay attention. And remember that some waters do not announce their intentions clearly. It was against this backdrop of quiet warnings and accumulated experience that official interest deepened. When the Japanese government finally took notice in a more structured way, it was not responding to myth alone, but to a long-standing pattern of caution embedded in maritime culture. A pattern that had been forming long before anyone thought to give it a name. For many years, the unease surrounding the Devil's Sea existed in a space that governments tend to overlook. It lived in local knowledge, in insurance adjustments, in unspoken decisions made by captains and fishermen. These signals rarely rise high enough to trigger official response. Governments respond to numbers, to incidents that cross thresholds, to patterns that can be defended publicly. Quiet avoidance does not usually qualify. That changed in the years following the Second World War. Japan in the late 1940s and early 1950s was rebuilding not just its cities, but its systems of knowledge and control. Maritime activity was essential to that recovery. Fishing fleets needed to expand. Trade routes had to be restored. Scientific research was increasingly seen as a symbol of national renewal and competence. The sea was no longer just a source of livelihood. It was a domain that needed to be understood, managed, and made safer through modern methods. It was during this period that the accumulation of losses in the region east of Japan's coast began to attract formal attention, not because of one catastrophic event, but because the disappearances refused to stop entirely, even as navigation improved elsewhere. Reports crossed desks that were difficult to categorize, fishing vessels missing without distress calls, patrols finding nothing, weather records that did not fully align with outcomes. Individually, none of these demanded escalation. Together, they became harder to dismiss. Within the Japanese government, responsibility for maritime safety was distributed across several agencies. Fisheries oversight, coastal defence, scientific research and transportation all intersected at sea. This diffusion of responsibility often slows response. No single authority feels empowered to declare a problem unless evidence is overwhelming. In the case of the Devil's Sea, evidence was suggestive rather than conclusive. What tipped the balance was not public pressure, but internal concern. Officials began to notice that certain reports shared similarities that were difficult to explain away as coincidence. Losses clustered geographically. Investigations stalled repeatedly for the same reasons. The phrase "cause unknown" appeared too often in final summaries. At the same time, Japan was investing heavily in scientific credibility. Oceanography, geology, and meteorology were fields seen as strategically important. Understanding the surrounding seas was not just about safety, but about asserting competence and sovereignty. Allowing a stretch of nearby ocean to remain poorly understood carried political as well as practical implications. Eventually, a decision was made to investigate more directly. Rather than issuing public warnings or altering official charts immediately, the government chose a measured approach. A research mission would be sent into the region to gather data. The goal was not to confirm legends, but to identify environmental hazards that could explain the reported incidents. This framing was deliberate. It allowed officials to proceed without endorsing fear or speculation. The vessel selected for this task was equipped with modern instruments for the time. It carried trained scientists, not just sailors. Its mission was to observe, measure, and report. The expectation was that the sea would yield to systematic study, as it had in so many other places. The decision to send a research vessel into the Devil's Sea marked a subtle but important shift. It signalled that informal warnings had reached a level where they could no longer be ignored. It also reflected confidence. Confidence that science could bring clarity where tradition had only offered caution. The mission did not return. The loss of a government-backed research vessel was a shock that reverberated through multiple layers of administration. Unlike fishing boats or private ships, this was an official asset. Its disappearance demanded explanation. Yet once again, the familiar problem emerged. There was little to examine. No confirmed wreckage, no survivors, no clear sequence of events that could be reconstructed with confidence. Internal investigations began immediately. Weather conditions were reviewed, communication logs examined, equipment specifications analysed. Each avenue produced partial answers but no definitive conclusion. Environmental instability was cited. Volcanic activity was mentioned. Rough seas were acknowledged. None of these explanations fully accounted for the absence of evidence. For government officials, this presented a dilemma. Acknowledging that a research vessel had vanished in nearby waters without explanation risked public concern. Downplaying the incident risked internal credibility. The response had to balance transparency with reassurance. Publicly, statements emphasized the inherent dangers of ocean research. Privately, concern deepened. The loss changed how the Devil's Sea was discussed within official circles. It was no longer merely a region associated with anecdotal loss. It had claimed a symbol of state competence. That fact could not be easily set aside. In response, the government took several quiet steps. Research into submarine geology in the region was expanded. Existing data was re-examined. Navigation advisories were reviewed internally, even if not immediately altered. There was no dramatic announcement declaring the area dangerous. Instead, caution seeped into planning processes. One of the challenges officials faced was the lack of clear policy options. Closing off a stretch of ocean was impractical. Issuing strong warnings without conclusive evidence risked economic consequences, particularly for fishing communities. Doing nothing risked further loss. The compromise was research. Additional studies were commissioned, often framed broadly as oceanographic surveys rather than targeted investigations of danger. This allowed data to be gathered without drawing attention to specific concerns. It also reflected a hope that the environment could be understood well enough to reduce risk without restricting access. At the same time, information began to circulate more freely between agencies. Reports that might once have remained siloed were shared. Patterns were compared. The Devil's Sea emerged not as a single problem, but as a convergence of multiple hazards. Geological instability, complex currents, potential magnetic irregularities. Each was manageable in isolation. Together they created uncertainty. This shift in perspective was significant. Rather than asking what mysterious force caused disappearances, researchers began asking how ordinary processes interacted in unusual ways. This reframing aligned with scientific norms and allowed progress without sensationalism. However, the shadow of the lost research vessel lingered. It served as a reminder that even well-equipped missions were vulnerable. That reminder influenced risk assessments in subtle ways. Expeditions planned routes more conservatively. Contingency plans grew more detailed. Redundancy became a priority. From the outside, these changes were invisible. The Devil's Sea did not suddenly acquire warning markers or restricted zones, but internally it was no longer treated as just another patch of ocean. The government's response also reflected broader cultural attitudes toward uncertainty. In Japan, acknowledging risk does not always require public declaration. Precaution can be implemented quietly, through consensus and gradual adjustment. This approach can appear opaque to outsiders, but it is effective at reducing panic while allowing adaptation. As years passed, the rate of high-profile incidents declined. This was often cited as evidence that the danger had been overstated. Yet within government agencies the interpretation was different. Improved awareness and avoidance were credited. The environment itself had not necessarily become safer. Behaviour had changed. The Devil's Sea became a kind of test case for how governments manage poorly understood risk. It demonstrated the limits of reactive policy. Waiting for definitive proof before acting can be costly when evidence is difficult to obtain. Acting too aggressively without proof can be equally damaging. The balance struck was imperfect, but it reflected a recognition that not all hazards announce themselves clearly. Some require ongoing attention rather than resolution. The involvement of the government also had an unintended consequence. It legitimised the concern. Once state resources were devoted to studying the region, it was harder to dismiss stories as mere folklore. Even without dramatic statements, the act of investigation signalled that something warranted scrutiny. This legitimacy, in turn, attracted international interest. Researchers outside Japan began to ask questions. Comparisons with other regions intensified. The Devil's Sea entered global conversations about maritime risk and environmental complexity. Yet within Japan, discussion remained restrained. The focus stayed on understanding processes rather than naming threats. The loss of the research vessel was acknowledged, but not mythologized. It became part of a broader effort to map and monitor a challenging environment. As technology advanced, so did expectations. Satellites promised better oversight, sensors promised earlier warnings, but each new tool also revealed new layers of complexity. The ocean floor was more active than previously believed. Chemical processes were more dynamic, models required constant revision. In this context, the government's decision to take notice appears less like a dramatic turning point and more like the beginning of a long, cautious engagement. One that continues quietly, adapting as knowledge grows and assumptions are challenged. The Devil's Sea did not become safer because it was acknowledged. It became better respected. That distinction matters. Respect implies limits. It accepts that understanding may be incomplete and that caution must persist even as explanations improve. As research deepened, attention increasingly turned downward, toward the seabed itself. The question shifted again. What exactly lay beneath this water? How active was the volcanic landscape below? And how might processes hidden far from the surface be shaping events above in ways that are still difficult to anticipate? Those questions would lead investigators into a realm where the sea's quiet surface concealed a far more restless world, one that offered new clues and new challenges in equal measure. By the time the research vessel was dispatched, the Devil's Sea was no longer just a subject of whispered caution among fishermen or a cluster of ambiguous reports in maritime files. It had become a question mark that the Japanese government could no longer leave unanswered. Sending a scientific mission into the region was meant to do what careful observation usually does: replace unease with data, replace rumour with measurement, replace absence with understanding. The ship itself was not unusual for its time. but it was purpose-built for inquiry rather than commerce. It carried scientists trained to observe volcanic activity, ocean currents, and geological structure. It carried instruments designed to detect changes beneath the surface, not just weather above it. It was crewed by professionals who understood both the sea and the responsibility of an official mission. Nothing about the expedition suggested recklessness. The vessel departed under conditions that did not raise alarms. There was no immediate storm warning, no extraordinary weather forecast. Communication protocols were standard for the era. The mission plan was conservative. Its task was to survey volcanic activity in waters south of Tokyo, an area already known to sit atop unstable geology. The goal was straightforward: gather information, return safely, expand knowledge, then contact was lost. The first hours after communications ceased were not filled with panic. Delays happen at sea. Signals fade temporarily. Equipment malfunctions. Crews troubleshoot. Ships reappear on schedules that drift slightly. It was only when expected check-ins passed without explanation that concern began to build. Search efforts were initiated cautiously at first, then with growing urgency. Patrol vessels combed likely routes. Aircraft scanned the surface. Nearby traffic was questioned. Weather data was reviewed repeatedly, as if re-examination might reveal something previously overlooked. Nothing surfaced. No debris, no oil slick, no lifeboats, no confirmed sightings. What made this disappearance especially unsettling was its context. This was not a ship that vanished in ignorance of risk. It was there specifically to study instability. Its crew was prepared to observe unusual conditions. If any vessel should have been capable of identifying emerging danger and responding appropriately, it was this one. The absence of evidence forced investigators into familiar but uncomfortable territory. They began listing plausible scenarios without being able to privilege one over another. Sudden volcanic activity could have disrupted the vessel. A rapid release of gas from the seabed might have altered buoyancy. A localized magnetic disturbance could have interfered with navigation at a critical moment. Rough seas could have overwhelmed the ship without leaving surface debris. Each explanation had merit. None could be confirmed. Internally, the disappearance triggered intense scrutiny. Mission planning documents were reviewed line by line. Instrument specifications were analysed to determine what data might have been lost with the ship. Communication protocols were examined for weaknesses. The goal was not just to understand what happened, but to prevent it from happening again. Yet prevention depends on clarity, and clarity was precisely what this incident denied. The loss of a research vessel carries symbolic weight. It undermines the assumption that knowledge confers control. Science is often framed as a way to reduce uncertainty, to make the unknown manageable. When a scientific mission itself becomes part of the unknown, the narrative shifts. The tools designed to illuminate risk are revealed to be vulnerable to it. For the families of the crew, the absence was devastating in a more immediate way. Without wreckage or confirmed cause, grief had no anchor. Official statements acknowledged loss but offered little explanation. The sea, once again, provided no closure. Public discussion of the incident was restrained. Authorities avoided dramatic language. The emphasis remained on the inherent dangers of ocean research. This was not inaccurate, but it was incomplete. The specific conditions of the Devil's Sea were rarely highlighted explicitly. Doing so risked amplifying fear or inviting speculation. Within scientific circles, however, the disappearance was impossible to ignore. It became a reference point in discussions about the region, a reminder that the environment did not always yield to careful planning, that even targeted investigation carried risk. One of the most troubling aspects of the incident was the lack of transitional evidence. In many maritime accidents, there is a sequence: a distress call, a report of trouble, a last known position. Here, the record seemed to stop abruptly. This suggested either a rapid event or a failure cascade so sudden that response was impossible. Researchers began re-examining what kinds of processes could produce such outcomes. Attention turned increasingly toward the seabed. The Devil's Sea lies above a complex network of submarine volcanoes, some active, some dormant, some poorly mapped. Eruptions in deep water do not always produce dramatic surface effects. Instead, they can release heat and gases that alter the physical properties of surrounding water. One theory proposed that a sudden release of volcanic gas could create a zone of reduced water density. A vessel entering such a zone might experience a rapid loss of buoyancy. Unlike waves or storms, this process would offer little warning and leave minimal debris. The ship could sink quickly and intact, carrying evidence with it to depths difficult to explore. Another possibility involved underwater landslides triggered by seismic activity. The movement of large volumes of sediment could generate powerful localized disturbances, including waves and pressure changes. A ship caught directly above such an event might be overwhelmed without time to react. Magnetic irregularities also remained under consideration. The geological composition of the region includes materials capable of distorting magnetic fields. While such distortions are usually subtle, in combination with other factors, they could contribute to navigational error. A small deviation at the wrong moment could place a vessel over particularly unstable ground. None of these theories alone fully satisfied investigators. What troubled them was the convergence. The Devil's Sea appeared to host multiple risk factors that could interact unpredictably. A vessel passing through might encounter not one hazard, but several in rapid succession. This compounded risk reduces the margin for recovery. The disappearance of the research vessel forced a reconsideration of assumptions about monitoring. Instruments designed to detect gradual changes may not capture sudden events. Sensors placed on ships are limited to the ship's survival. When the vessel is lost, so is the data. This creates a paradox. The most dangerous events are also the hardest to observe directly. In the years following the incident, this paradox influenced how oceanographic research was conducted. There was increased interest in remote sensing. Instruments placed on the seafloor or deployed independently of ships offered a way to gather data without risking crews. Autonomous systems began to seem more attractive, though they too faced challenges in unstable environments. The incident also affected how future missions were planned. Routes were adjusted, time spent in certain areas was minimized. Redundancy became a guiding principle. Communication systems were diversified. These changes reflected a quiet acknowledgement that the region demanded extra caution. Internationally, the disappearance attracted attention among researchers studying maritime risk. Comparisons were drawn to other unexplained losses, but the Devil's Sea stood out because of its geological context. The idea that undersea processes could directly influence surface safety gained traction. This broadened discussions about how oceans are studied and navigated. Despite this increased attention, the fate of the vessel itself remained unresolved. Over time, it became a reference rather than an active investigation. New generations of researchers learned about it as a case study, a reminder of uncertainty rather than a puzzle awaiting solution. This unresolved status contributes to the enduring unease surrounding the Devil's Sea. The loss is not just historical, it represents a boundary of knowledge that has not been crossed, a moment where inquiry encountered its own limits. It is important to note that this incident did not halt research in the region. If anything, it sharpened focus. Understanding the conditions that led to the disappearance became a priority, not to assign blame, but to reduce future risk. That focus led scientists deeper into the study of submarine volcanoes, tectonic movement, and chemical processes occurring far below the surface. The sea was no longer viewed solely as a surface environment influenced by weather and currents. It was understood as an interface, shaped by forces rising from below. The research vessel that vanished did not deliver the data it was meant to collect, but its loss reshaped the questions being asked. Instead of assuming that danger would announce itself in familiar ways, scientists began considering the possibility that the most significant threats were invisible until they acted. This shift in perspective would have lasting consequences, It influenced how the Devil's Sea was conceptualized, not as a singular mystery, but as a complex system where multiple hidden processes intersect. Understanding those processes required new tools, new models, and a willingness to accept that some environments resist simple explanation. As attention continued to turn toward the geology beneath the waves, the narrative moved away from disappearance itself and toward what might be responsible for it. The question was no longer just why ships failed to return, but what kind of landscape lay beneath them, shaping events silently and relentlessly, long before any vessel crossed its surface. From the surface, the Devil's Sea gives very little away. The water rolls and reflects light much like any other part of the Western Pacific Ocean. There are days when it appears calm enough to invite confidence, when the horizon lies flat and uninterrupted, and nothing suggests that anything unusual is happening below. But the character of this region is not defined at the surface. It is defined by what lies beneath it, in a landscape shaped not by wind or waves, but by heat, pressure, and constant geological tension. Beneath these waters is one of the most active and complex volcanic environments on the planet. The Devil's Sea sits along the edge of what geologists call the Ring of Fire, a vast arc of tectonic instability that wraps around much of the Pacific Basin. This is where massive plates of the Earth's crust collide, slide beneath one another, and grind slowly but relentlessly, releasing energy that reshapes the planet over time. Earthquakes, volcanoes, deep trenches, and sudden seafloor collapse are not anomalies here. They are the baseline. Japan itself exists because of this activity. The islands were formed by volcanic processes driven by subduction, where one tectonic plate is forced beneath another. The same forces that built the land continue offshore, extending far beneath the ocean's surface. The Devil's Sea occupies a section of this boundary where several plates interact in particularly complicated ways. It is not a single fault line or a neat geological feature. It is a crowded intersection of stresses. The seafloor here is uneven, fractured, and in constant motion, even when that motion is too slow or too deep to be felt directly. Submarine volcanoes dot the region, some towering thousands of meters from the ocean floor, others smaller and more numerous, rising and collapsing over geological time. Some are well mapped, others are inferred from seismic readings and chemical signatures rather than direct observation. Unlike volcanoes on land, submarine volcanoes rarely announce themselves dramatically. There is no plume of ash visible from miles away, no lava fountain lighting up the night sky. Most eruptions happen quietly, muffled by immense pressure. Lava flows into cold water and solidifies rapidly. Gas dissolves into the surrounding sea. The surface may remain undisturbed. This quietness is deceptive. When a submarine volcano becomes active, it can alter its environment in ways that are subtle but profound. Heat released into surrounding water changes local temperature gradients. Gases released from magma, including carbon dioxide and methane, can dissolve or form bubbles depending on pressure and depth. These processes can occur suddenly and locally, creating pockets of water with properties very different from the surrounding sea. Water density matters more than most people realize. Ships float because water pushes back with enough force to support their weight. That force depends on density. If the density of the water beneath a vessel drops abruptly, buoyancy drops with it. In extreme cases, a ship can lose support faster than it can compensate. The idea that gas release from the seabed could affect buoyancy has been debated, tested, and modelled. It is not universally accepted as a primary cause of ship loss, but it is taken seriously enough to be studied. In regions like the Devil's Sea, where volcanic activity is ongoing and poorly mapped, the possibility cannot be dismissed outright. Adding to this complexity is the shape of the ocean floor itself. The region contains deep trenches and steep slopes where sediment can accumulate unstably. Earthquakes, even small ones, can trigger underwater landslides. These movements displace massive volumes of material generating localized disturbances in the water column above. Such events can create powerful but short-lived effects: sudden changes in pressure, turbulence rising from below, waves that form without travelling long distances. A vessel passing overhead at the wrong moment might experience forces that are difficult to predict or counter, especially if the event occurs directly beneath it. One of the challenges scientists face is that these processes do not leave neat signatures. A landslide may settle quickly. Gas bubbles dissolve or disperse, lava flows cool and blend into existing rock. By the time investigators arrive, the evidence has often been erased or buried. The ocean floor is both the source of disturbance and an efficient archivist that hides its own records. Mapping this environment is difficult even with modern technology. Sonar surveys provide snapshots, but the terrain changes. New volcanic cones form, old ones collapse, sediment shifts. What was accurate a decade ago may already be outdated. Continuous monitoring is expensive and technically challenging, especially in deep water. This dynamic landscape has earned the region a grim nickname among some geologists, a volcanic graveyard, not because it is lifeless, but because it is crowded with the remnants of past eruptions. Collapsed cones, fractured ridges, fields of hardened lava piled atop one another in irregular patterns. It is a terrain shaped by repeated creation and destruction. For vessels passing above, this instability translates into unpredictability. Currents can be affected by temperature differences caused by geothermal heat. Chemical changes in the water can influence how sound travels, complicating sonar readings. Magnetic properties of volcanic rock can distort local magnetic fields, interfering subtly with navigation instruments. Each of these effects on its own might be manageable. Combined, they create an environment where small problems can compound quickly. A slight navigational error, a momentary loss of signal, a change in sea state that does not match the forecast. These are not dramatic failures. They are the kinds of disruptions that crews handle routinely. What makes the Devil's Sea different is how often multiple disruptions appear together. The research vessel that vanished was sent precisely to study this environment. Its loss underscored how little margin for error exists when operating above such an active seafloor. The ship did not need to encounter a catastrophic eruption. A minor event at the wrong time could have been enough. Geological records indicate that the region has experienced numerous submarine eruptions over the past centuries. Some have been large enough to create new islands temporarily, only for them to erode or collapse back into the sea. Others have left no surface trace at all. These events remind researchers that the seafloor here is not static. It is alive with processes that unfold on timescales ranging from seconds to millennia. One of the more unsettling aspects of this activity is how poorly it aligns with human expectations of warning. On land, volcanic monitoring relies on visible signs, ground deformation, gas emissions, seismic swarms. At sea, many of these signals are harder to detect. Instruments must be placed directly on the seabed or suspended in the water column. Data transmission is slower and more fragile. Coverage is incomplete. This means that eruptions or gas releases can occur without immediate detection. By the time changes are noticed, the event may already be over. For a ship passing overhead, that delay is irrelevant. The effect has already been felt. The Devil's Sea challenges the assumption that danger must be visible to be real. Its hazards originate in darkness, under kilometers of water, driven by forces indifferent to surface conditions. Calm seas do not guarantee safety. Clear skies do not predict stability below. This realization has influenced how scientists think about maritime risk more broadly. It highlights the importance of subsurface processes in shaping surface safety. It suggests that some regions require a fundamentally different approach to monitoring and navigation. Understanding this volcanic graveyard is not about eliminating risk entirely. That is not possible. It is about recognizing that certain environments operate with tighter tolerances, that the ocean floor can shape events above it in ways that are sudden and difficult to predict. As research has continued, attention has shifted toward integrating geological data with oceanographic models. Rather than treating the sea as a surface phenomenon, influenced primarily by weather and currents, scientists increasingly view it as a vertical system where events far below can propagate upward rapidly. This shift has practical implications. It informs route planning. It shapes the placement of sensors. It influences how warnings are issued and interpreted. It also tempers confidence. The Devil's Sea is not dangerous because it is mysterious. It is dangerous because it is active. The volcanic landscape beneath these waters is not malicious. It does not target ships. It simply does what geology does, releasing energy where stress accumulates. The problem is that human systems are not always designed to accommodate that behaviour. As long as tectonic plates continue to move, the Devil's Sea will remain restless. Volcanoes will continue to form and collapse. The seafloor will continue to shift. These processes do not care whether a ship passes overhead, but when they intersect with human activity, the consequences can be severe. This understanding reframes the region's reputation. The Devil's Sea is not an anomaly in an otherwise stable ocean. It is a reminder of how dynamic the planet truly is, even in places that appear calm. Its danger lies not in the unknown, but in the known processes that are difficult to observe and harder still to predict in real time. As scientists probe deeper into this volcanic graveyard, they uncover not just explanations for past losses, but new questions about how much we can ever know about environments shaped by constant change. And those questions, once raised, do not stay confined to one stretch of water. They ripple outward, influencing how we think about risk, technology, and our place above a planet that is still very much in motion. For sailors and scientists alike, instruments are extensions of trust. They translate invisible forces into readable signals, turning vast, shifting environments into something navigable. A compass needle pointing north, a gyro holding steady, a radio signal confirming position. These tools do not eliminate danger, but they create a shared frame of reference. When they work, confidence follows. When they don't, uncertainty multiplies. In the Devil's Sea, reports of instruments behaving strangely surfaced early and persisted quietly. Not dramatic failures, not explosions of sparks or screens going dark, but subtler problems. Compasses drifting, readings disagreeing with one another, navigation systems requiring constant correction. Crews noticing that their instruments technically functioned, yet no longer felt trustworthy. This distinction matters. An instrument that fails outright is easier to respond to. Procedures exist for that. Redundancies are activated. Emergency protocols are followed. An instrument that works inconsistently creates a different kind of problem. It forces crews to decide, moment by moment, whether to trust what they are seeing or what they are feeling. That hesitation can be dangerous. Magnetism is one of the oldest tools of navigation. Long before satellites or digital displays, sailors relied on the predictable behaviour of Earth's magnetic field. While that field is not perfectly uniform, its variations are usually gradual and well mapped. Charts account for known deviations, compasses are corrected accordingly. Most of the time, this system works remarkably well. In regions with complex geology, however, magnetism becomes less predictable. Certain types of rock, particularly those formed through volcanic processes, can retain strong magnetic signatures. When these rocks are present in large quantities beneath the seabed, they can distort the local magnetic field. The result is not necessarily a dramatic reversal, but enough deviation to introduce error. The Devil's Sea sits above a seafloor rich in volcanic material. Lava flows, hardened over time, contain minerals capable of influencing magnetic readings. These formations are irregular. They are not evenly distributed. As a vessel moves over them, the magnetic environment can change subtly and rapidly. This creates a challenging situation for navigation. A compass might indicate a heading that is technically correct relative to local magnetism, but incorrect relative to true north. Modern systems often compensate for this, but compensation relies on models. Models assume stability. In an environment where the seafloor itself is shifting and magnetic anomalies are poorly mapped, those assumptions weaken. Reports from crews operating in the region described needing to recalibrate frequently. Gyroscopic systems designed to maintain orientation independently of magnetism sometimes conflicted with magnetic readings. GPS, when available, offered a third reference point, but early systems lacked the precision and reliability crews expect today. When three sources disagree, decision-making slows. For scientists studying these reports, the challenge lay in separating perception from physics. Humans are quick to attribute confusion to external forces when under stress. Fatigue, poor visibility, and rough seas can all affect judgment. But when similar accounts emerged from different crews, across different years, patterns began to stand out. One recurring observation was that instrument issues often coincided with otherwise unremarkable conditions: clear weather, moderate seas, no obvious mechanical failure. Crews would notice discrepancies without an accompanying explanation. These moments did not always lead to disaster, but they left an impression. From a technical standpoint, magnetic anomalies do not need to be extreme to be disruptive. A few degrees of deviation can matter, especially in regions with narrow margins for error. When combined with strong currents, complex seafloor topography, and limited visibility, small errors accumulate. Communication instruments also featured in these accounts. Radios crackling unexpectedly, signals fading and returning without clear cause. Again, not total failure, but interruption. In an age before satellite communication was widespread, radio was lifeline and reassurance. Interference, even brief, heightened anxiety. Some researchers have suggested that ionized gases released from submarine volcanic activity could contribute to radio interference. While this remains an area of ongoing study, it aligns with the broader theme of subsurface processes influencing surface conditions. The ocean is not a barrier to energy transfer. It is a medium through which physical effects propagate. Instrument panels themselves became points of focus. Engineers examined logs for anomalies. Power systems were scrutinized. In many cases, no faults were found. The instruments functioned within specifications. The problem appeared to be environmental rather than mechanical. This distinction is important. It suggests that the instruments were not broken in the conventional sense. They were being asked to operate in conditions they were not fully designed to handle. Their limitations were being exposed not by malfunction, but by context. The research vessel that vanished added weight to these concerns. As a scientific ship, it carried more instruments than most commercial vessels. Its loss raised questions about whether data collected in its final moments might have revealed anomalies that could not be transmitted in time. The idea that crucial information might have existed briefly and then disappeared with the ship underscored the fragility of observation in such environments. Modern navigation systems have reduced many of these risks but not eliminated them. GPS relies on satellite signals that can be affected by atmospheric conditions and interference. Magnetic compasses remain as backups, but they are subject to the same distortions. Electronic systems add layers of complexity, each with its own vulnerabilities. In the Devil's Sea, redundancy does not always guarantee clarity. Multiple systems may be influenced simultaneously by the same environmental factors. When that happens, confidence erodes quickly. Crews are forced to rely on judgment, experience, and incomplete information. This reliance on human perception reintroduces the role of intuition, long emphasized by fishermen and sailors in the region. Experienced mariners often report that when instruments and instincts diverge consistently, they trust their instincts. This is not superstition. It is pattern recognition developed over years. The problem arises when less experienced crews lack that internal reference. Training addresses some of this gap, but no training can fully replicate the feeling of operating in an environment where feedback is inconsistent. Stress increases. Decision-making slows. Small mistakes become more likely. From a scientific perspective, these conditions complicate data collection. Instruments deployed to measure magnetic fields, currents, and chemical composition must be calibrated carefully. Interference can corrupt readings. Distinguishing between true environmental signals and noise becomes more difficult. The result is data that requires cautious interpretation. This caution sometimes frustrates those seeking definitive answers. Why can't scientists simply measure what's happening? The answer lies in scale and variability. The processes influencing magnetism and instrumentation in the Devil's Sea are localized and transient. They may occur over minutes or hours, across distances too small to be captured by sparse sensor networks. Capturing these events requires dense monitoring, continuous observation, and significant resources. Even then, some phenomena may evade detection simply because they are brief. This creates a paradox. The most disruptive events are the hardest to observe. The history of navigation in the region reflects this challenge. As instruments improved, some types of accidents decreased, others persisted. The pattern shifted but did not disappear. This suggests that while technology mitigates risk, it cannot fully compensate for environmental complexity. The phrase broken instruments can be misleading. It implies failure where there may be none. In the Devil's Sea, instruments often function as designed. They simply encounter conditions outside their optimal range. This distinction matters for how risk is managed. Acknowledging this limitation requires humility. It means accepting that even advanced systems have boundaries, that some environments test those boundaries regularly. That safety depends not just on technology, but on understanding where technology's assumptions break down. Researchers studying magnetic anomalies in the region have emphasized the need for updated mapping. The seafloor's magnetic signature changes over time as volcanic activity continues. Static charts become outdated. Maintaining accuracy requires ongoing measurement. This is expensive and logistically challenging, especially in deep water. Despite these challenges, progress has been made. Better models exist today than in the past. Awareness of magnetic complexity informs route planning. Crews are trained to expect discrepancies and respond accordingly. These adaptations reduce risk, but they do not eliminate it. What remains unsettling is how these instrumental issues intersect with other hazards. A magnetic anomaly alone may be manageable. Combined with sudden sea state changes or buoyancy effects, it becomes part of a cascade. Understanding these cascades is an ongoing focus of research. The Devil's Sea exposes the interconnectedness of systems. Geology influences magnetism. Magnetism influences navigation. Navigation influences exposure to other hazards. Failure does not occur in isolation. It emerges from interaction. This perspective shifts the narrative away from mystery toward complexity. The sea does not confound instruments out of malice or randomness. It presents conditions that challenge assumptions embedded in design. Recognizing this reframes fear as a call for adaptation rather than resignation. As attention continues to move between surface behavior and subsurface processes, instruments remain central to the story. They are both tools and participants. Their struggles reflect the environment's demands. Understanding why instruments behave unreliably here is not just about preventing loss in one region. It informs how navigation and monitoring systems are designed globally. It highlights the need for flexibility, redundancy, and respect for environments that do not conform neatly to models. The Devil's Sea, in this sense, is not an exception. It is an early warning, a place where the limits of our tools become visible, and when those limits are revealed, they prompt a deeper question. Not just how to fix instruments, but how to operate safely in environments where certainty is always provisional. One of the most unsettling possibilities considered by scientists studying the Devil's Sea does not involve storms, waves, or even volcanic eruptions in the dramatic sense. It involves something far quieter and far more difficult to perceive from the surface: gas. Specifically, methane trapped beneath the ocean floor, waiting under pressure for conditions that allow it to escape. Methane is a simple molecule common throughout the planet, produced by biological processes and geological ones alike. On land, it leaks from wetlands, seeps from rock formations, and occasionally announces itself in dramatic ways, such as gas eruptions or fires. Beneath the sea, methane behaves differently. Immense pressure and low temperatures can lock it into solid structures known as methane hydrates, ice-like formations that trap gas molecules inside cages of frozen water. These hydrates are stable only under very specific conditions. Change the temperature, change the pressure, disturb the sediment that holds them in place, and they can break down rapidly, releasing large volumes of gas into the surrounding water. The Devil's Sea sits in a region where all the ingredients for this process exist: tectonic instability, submarine volcanic heat, thick layers of sediment on steep slopes. It is an environment where methane can accumulate quietly for long periods, and then be released suddenly without warning. From the surface, such a release would be invisible. Methane rising through water does not necessarily break the surface in dramatic plumes. Much of it dissolves or disperses before reaching open air. What it does do, however, is change the physical properties of the water column as it rises. Gas bubbles mixed into water reduce its overall density, and density once again is everything when it comes to buoyancy. A ship floats because it displaces a volume of water equal to its weight. If the water beneath it suddenly becomes less dense, that balance is disrupted. The ship does not gradually settle lower. It can lose support abruptly. In extreme scenarios, a vessel could experience what feels like the sea opening beneath it, not violently, but decisively. This concept has been tested experimentally. Large tanks of water infused with gas show a clear reduction in buoyant force. Objects that float easily in normal water can sink rapidly when gas concentration increases. The physics is not speculative. What remains uncertain is scale and frequency in real ocean environments. Critics of the methane theory often point out that for a large ship to sink purely due to gas release, the volume of gas would need to be substantial and localized. They are correct. Such events are likely rare, but rarity does not equal impossibility, especially in regions where geological conditions make accumulation more likely. The Devil's Sea is one such region. Seismic surveys and chemical analyses have identified methane deposits beneath parts of the Western Pacific Ocean. These deposits are not unique to this area, but they are significant. Combined with volcanic heat sources, they create the potential for destabilization. An undersea eruption does not need to reach the surface to trigger gas release. Heat alone can be enough. One of the most disturbing aspects of this mechanism is how little warning it provides. There is no gradual build-up visible from above, no darkening clouds, no change in wind. A ship could pass over stable hydrates for years without incident, then, on one unlucky crossing, encounter a zone where gas is rising rapidly through the water column. For a crew on deck, the experience would be confusing and terrifying. The sea might appear calm. Instruments might not register anything unusual until it is too late. The ship could begin to list or settle unexpectedly. Engines would struggle against altered resistance. There would be little time to understand what was happening, and once the ship sank, evidence would be scarce. Gas bubbles dissipate quickly. Water returns to normal density. The seabed event that triggered the release may leave only subtle traces. Wreckage, if it sinks intact, may descend rapidly into deep trenches or unstable terrain. From the surface, it would appear as though the ship simply vanished. This aligns uncomfortably well with some of the historical reports from the Devil's Sea. Vessels lost without distress calls, no prolonged struggle, No debris fields spreading over miles, just absence. Methane release is not the only mechanism capable of producing sudden buoyancy loss. Other gases, such as carbon dioxide, can behave similarly under certain conditions. The key factor is rapid change. Ships are designed to handle waves, wind, and gradual flooding. They are not designed for the water itself to stop behaving like water. Adding to this risk is the uneven distribution of methane deposits. These hydrates do not form neat layers. They accumulate in pockets, along faults, and within unstable sediment. This creates a patchwork of potential risk zones. A vessel might pass safely through one area and encounter danger a short distance away. Detecting these zones in advance is extremely difficult. Sonar can identify some sediment structures, but gas hydrates do not always present clear signatures. Chemical sensors can detect dissolved gases, but coverage is sparse and data is not continuous. By the time elevated gas levels are measured, the event may already be underway. This uncertainty challenges traditional approaches to maritime safety. Warnings are typically issued based on forecastable hazards. Storms can be tracked, currents modelled, even volcanic activity can sometimes be anticipated through seismic monitoring. Methane release, particularly when triggered by subtle changes below the seabed, resists this kind of prediction. The sea, in these moments, does not become violent. It becomes unreliable. Some researchers have described this phenomenon as a sudden sea, not because waves rise abruptly, but because the fundamental assumptions about support and stability no longer hold. The surface may remain deceptively calm while the physics beneath it shifts. Skepticism around this explanation is healthy. Science advances through challenge. Many disappearances attributed to methane release may have other causes. Weather records may be incomplete. Human error may play a role. Mechanical failure cannot be ruled out. The danger lies not in proposing one explanation as definitive, but in ignoring it entirely because it feels unfamiliar. In regions without significant methane deposits, this mechanism is unlikely to matter. In regions like the Devil's Sea, it becomes part of a broader risk profile. One hazard among several. Rare, but potentially catastrophic. This layered risk is what makes the region so difficult to manage. Ships are not navigating a single threat, but a convergence. Volcanic heat destabilizing sediments, gas release altering buoyancy, magnetic anomalies confusing instruments, currents and waves behaving inconsistently due to temperature gradients. None of these require dramatic failure on their own. Together they narrow the margin for recovery. From an engineering perspective, designing ships to withstand such conditions is challenging. You cannot reinforce against water losing density. You cannot outrun a buoyancy collapse. Prevention depends on avoidance, not resistance. That means knowing where and when such events are likely, information that remains incomplete. Modern research has begun to focus on mapping methane hydrate deposits more precisely. Autonomous underwater vehicles survey the seabed. Chemical sensors monitor dissolved gas concentrations. Seismic networks track subtle movements that could destabilize sediments. These efforts improve understanding, but they are resource-intensive and geographically limited. Even with better data, uncertainty remains. Methane release does not follow a simple schedule. It responds to complex interactions between pressure, temperature, and geological stress. Climate change adds another variable, altering ocean temperatures and potentially affecting hydrate stability over long timescales. This raises uncomfortable questions. Could regions like the Devil's Sea become more dangerous in the future? Could changes beneath the ocean floor increase the frequency of sudden gas release? Scientists are cautious in their answers. The systems involved operate over long periods. Short-term prediction remains difficult. What is clear is that methane and buoyancy loss offer a plausible mechanism for some of the most baffling aspects of the Devil's Sea. They explain how ships might vanish quickly, why distress calls might not be sent, why debris might be minimal. They do so without invoking anything supernatural. At the same time, this explanation does not stand alone. It must be considered alongside other hazards. The sea does not rely on a single method to remind us of its power. It uses combinations. For mariners, the practical takeaway is not fear, but respect. Awareness that some dangers cannot be seen or sensed in advance, that calm conditions do not guarantee safety, that certain regions demand conservative planning, not because they are always dangerous, but because when they are, the consequences unfold too quickly for correction. For scientists, methane release represents a frontier where geology, chemistry and physics intersect in ways that challenge observation. Studying it requires patience, humility, and acceptance that some answers arrive slowly, if at all. The Devil's Sea has earned its reputation not through spectacle, but through these quiet mechanisms, through processes that do not announce themselves, through moments where the sea behaves differently, briefly, decisively, and then returns to normal as if nothing happened. And once the water settles, once density equalizes and bubbles dissolve, all that remains is the absence, a missing ship, an unanswered question, and the lingering realization that sometimes the most dangerous seas are the ones that look perfectly calm right up until the moment they are not. For most of maritime history, waves were understood as predictable things. They rose and fell in patterns shaped by wind, distance, and time. Sailors learned to read them the way farmers read clouds. Bigger storms meant bigger waves. Calm weather meant manageable seas. Even when conditions were rough, there was usually a rhythm to it, something you could anticipate if you watched closely enough. That assumption began to fracture in the 20th century, when reports surfaced of waves that did not behave according to any familiar rule. Walls of water appearing suddenly without warning in seas that were otherwise unremarkable. Not the long rolling swells of a distant storm, and not the chaotic chop of bad weather, but single towering waves that rose abruptly and vanished just as quickly. These came to be known as rogue waves. For a long time, they were dismissed as exaggerations or misperceptions. Sailors are tired, stressed, and operating in dangerous environments. Memories blur. Fear distorts scale. That was the prevailing attitude. After all, wave theory suggested that waves followed statistical distributions. Extreme outliers were theoretically possible, but so rare as to be practically irrelevant. A wave twice the significant wave height was already unlikely. 3 times was almost impossible, and yet ships kept reporting encounters that should not have happened. In the Devil's Sea, these reports carried particular weight. They aligned too well with disappearances that left little evidence behind. A rogue wave does not need hours to do damage. It does not announce itself with a changing sky. It does not require prolonged exposure. One moment is enough. Modern science now accepts that rogue waves are real. Satellite data, buoy measurements, and direct observation have confirmed their existence across the world's oceans, including the Western Pacific Ocean. What remains difficult is predicting when and where they will form. A rogue wave is not simply a very large wave. It is a convergence, multiple wave systems intersecting, currents amplifying energy, underlying topography focusing wave power upward instead of dispersing it. The result is a sudden spike in wave height that does not follow the surrounding pattern. The Devil's Sea provides an ideal environment for this kind of convergence. Currents in the region are complex and variable, influenced by temperature gradients, volcanic heat, and shifting seabed contours. Waves generated far away can intersect with locally generated waves in unpredictable ways. When these systems align just right, energy stacks vertically instead of spreading out. A wave grows rapidly, steepens, and rises. From the deck of a ship, the experience would be terrifying and brief. There is no gradual build-up, no warning swell. One moment, the sea behaves normally. The next, a wall of water looms where nothing existed seconds earlier. For large commercial vessels, the danger lies not only in being overtopped, but in structural stress. Modern ships are designed to withstand heavy seas, but they're not always designed for sudden vertical impact. A rogue wave striking head-on can exert enormous force. Windows can shatter, equipment can be torn loose, water can flood decks and compartments almost instantly. If the wave breaks directly onto the vessel, the impact can compromise stability. If it strikes from the side, it can induce a roll beyond recovery. Smaller vessels fare even worse. Fishing boats and research ships lack the mass and structural reinforcement of large cargo vessels. A single rogue wave could capsize them outright or disable critical systems before a distress call is sent. What makes rogue waves particularly unsettling in the context of the Devil's Sea is how well they explain certain absences. A ship struck by such a wave may not have time to communicate. Damage can be catastrophic in seconds. Debris may be minimal, especially if the vessel sinks intact or breaks apart in deep water. Unlike storms, rogue waves do not leave extended signatures. They are not tracked by weather systems. They do not persist. Once the energy disperses, the sea returns to its previous state. Investigators arriving later find no obvious evidence of what occurred. This transience complicates study. Buoys may miss the event entirely. Satellites may not be observing the exact location at the right moment. Crew reports, when they exist, are often the only testimony. In the Devil's Sea, there are fewer survivors to testify. Some researchers have proposed that undersea volcanic activity could contribute to rogue wave formation in the region. Heat released from the seabed alters local water density and current flow. Sudden disturbances can redirect energy upward. Steep underwater slopes can act like lenses, focusing wave power rather than dispersing it. This does not mean that every rogue wave in the region is caused by volcanic processes. It means that the environment increases the likelihood of unusual interactions. Rogue waves can occur anywhere, but some places make them more probable. The difficulty lies in separating coincidence from concentration. Rogue waves are rare by definition. Proving that a particular region produces them more frequently requires long-term, high-resolution data. That data is expensive and difficult to gather, especially in deep, unstable waters. Still, anecdotal evidence continues to accumulate. Crews report sudden extreme waves in otherwise moderate conditions. Damage patterns on ships that survive suggest impact forces inconsistent with normal seas. These accounts mirror reports from other rogue wave-prone areas of the world, lending credibility to the interpretation. For scientists, rogue waves challenge assumptions about risk modelling. Traditional wave forecasts focus on averages. They describe typical conditions, not extremes, but it is the extremes that cause catastrophic failure. Designing ships and planning routes based solely on expected conditions leaves little margin for events that fall outside the statistical norm. In the Devil's Sea, this margin is already thin. The presence of multiple hazards compounds the problem. A rogue wave alone is dangerous. Combined with magnetic confusion, buoyancy anomalies, or structural fatigue from previous stress, it becomes far more lethal. The sequence matters. A vessel disoriented by instrument discrepancies may present a vulnerable profile. A ship already riding lower due to altered buoyancy may be more easily overtopped. These cascading failures are difficult to reconstruct after the fact. Investigators may find evidence of water ingress or structural damage without knowing which event came first. Was the ship destabilized before the wave hit, or did the wave initiate the failure? Without survivors or data logs, certainty remains elusive. This uncertainty feeds the Devil's Sea's reputation. It creates a sense that the ocean here does not play by familiar rules. That danger arrives without warning. That preparation does not guarantee safety. From a human perspective, this is deeply unsettling. We are comfortable with threats we can see coming. Storms can be avoided or weathered, icebergs can be detected, pirates can be monitored, A single wave rising out of calm water violates our expectations of fairness and causality, and yet the physics behind rogue waves is indifferent to human comfort. It follows equations, not intuition. The sea does not need to escalate gradually. It can release energy all at once when conditions align. Modern monitoring systems have improved detection somewhat. High-frequency radar, satellite altimetry, and wave buoys provide better coverage than ever before. But coverage is not constant, and resolution is limited. Many rogue waves are still detected only after they have passed, inferred from damage rather than observed directly. This gap between detection and experience is crucial. It means that for mariners, rogue waves remain a threat that cannot be reliably anticipated in real time. Awareness helps, training helps, but neither eliminates risk. In regions like the Devil's Sea, where multiple factors increase unpredictability, this limitation becomes more pronounced. Crews operate knowing that some hazards cannot be forecast. That knowledge changes behaviour. Routes are adjusted. Time spent in certain areas is minimised. Conservative margins are applied. These adaptations reduce exposure, but they also acknowledge something fundamental. The ocean retains agency. Rogue waves do not require mystery to be terrifying. Their terror lies in their efficiency. They arrive fully formed, do their damage, and disappear. They do not linger to be studied. They leave behind only consequences. In the context of the Devil's Sea, they offer one more piece of a puzzle defined by suddenness and absence. They help explain how ships could be lost quickly, without prolonged distress or extensive debris. They fit into a pattern of hazards that operate below the threshold of anticipation. And yet, like methane release and magnetic anomalies, rogue waves are not an answer on their own. They are part of a system, a reminder that the sea is not a passive surface responding only to wind and weather, but a dynamic medium shaped by forces from below, from afar, and from interactions too complex to reduce to a single cause. As scientists continue to study these phenomena, they do so with an awareness that understanding does not equal control. Knowing that rogue waves exist does not prevent them. Mapping where they are more likely does not guarantee avoidance. What it does provide is context. It shifts disappearances from the realm of the inexplicable into the realm of the difficult. It replaces mystery with complexity. And while complexity is less satisfying than certainty, it is more honest. The Devil's Sea does not need legends to be dangerous. Physics is enough. Waves that rise without warning, driven by converging forces beneath a calm surface, are reminder enough that the ocean does not owe us gradual escalation. Sometimes it simply acts. From a distance, it seems like the problem should already be solved. Earth is wrapped in technology now. Satellites orbit continuously, scanning oceans, tracking storms, measuring temperatures, mapping currents, and relaying signals with extraordinary precision. We can watch hurricanes form days in advance. We can measure sea level changes down to millimeters. We can track ships anywhere on the planet in near real time. Against that backdrop, the idea that a stretch of ocean could still resist explanation feels almost anachronistic. And yet, the Devil's Sea continues to do exactly that. The difficulty is not that satellites fail outright. It is that they were never designed to answer the kinds of questions this region keeps asking. Satellites are exceptional at seeing broad patterns. They struggle with brief, localized subsurface events, and the Devil's Sea is defined almost entirely by those. Most satellite systems observe the ocean indirectly. They measure surface temperature, wave height averages, surface roughness, sea color, and gravitational variations. These measurements are invaluable for understanding large-scale behavior in the Pacific Ocean. They reveal currents stretching hundreds of kilometers. They show heat moving across basins. They track weather systems with stunning clarity. But the Devil's Sea does not misbehave at that scale. The hazards associated with this region are small in footprint and short in duration. A sudden gas release, a localized magnetic anomaly, a rogue wave forming from intersecting systems, an underwater landslide shifting pressure upward. These events can unfold over minutes, affect areas smaller than a satellite pixel, and leave no lasting surface signature. By the time a satellite passes overhead, the ocean has already returned to normal. Satellites follow fixed orbits. They revisit the same location on schedules measured in hours or days. Continuous observation is rare and limited to specific instruments and latitudes. Even when coverage exists, resolution is finite. A satellite might detect that something unusual happened after the fact, but not what happened or why. This creates a blind spot that feels counterintuitive. We think of satellites as omnipresent. In reality, they are intermittent observers, excellent at trends and averages, poor at surprises. The Devil's Sea thrives in those gaps. Take rogue waves as an example. Satellites can measure wave height statistically across large areas. They can tell us what the average wave conditions look like over time. But rogue waves are, by definition, outliers. They are single events rising sharply above the background state. Unless a satellite happens to be observing the exact location at the exact moment the wave forms, it will never be recorded. Methane release presents an even greater challenge. Gas bubbles rising through the water column alter density and buoyancy below the surface. Satellites cannot see that. They might detect subtle changes in surface roughness or temperature if the release is large enough and persistent enough, but many releases are neither. They occur deep, dissipate quickly, and leave no surface trace. Magnetic anomalies are similarly elusive. Satellites can measure variations in Earth's magnetic field at a broad scale, but the distortions relevant to ship navigation are often localized and transient. They may arise from specific seafloor structures or volcanic materials whose influence fades rapidly with distance. A satellite averages these effects over large areas, smoothing out the very irregularities that matter most. Even when satellites detect something unusual, interpretation is difficult. Data arrives stripped of context. A brief anomaly in surface temperature might reflect volcanic heat, a current shift, atmospheric effects, or instrument noise. Disentangling these possibilities requires corroborating data from other sources. In the Devil's Sea, corroboration is scarce. Surface buoys provide continuous data, but their placement is limited. Deep-sea sensors exist, but they are expensive, vulnerable, and few. Ships equipped with instruments pass through intermittently. When an event occurs between these observation points, it may go completely unrecorded. This patchwork of observation creates a frustrating reality. Scientists know that something is happening but cannot always capture it directly. They must infer processes from indirect evidence, from after effects, from patterns that emerge only when data is aggregated over long periods. This inference-based science is rigorous, but it lacks the satisfying clarity of direct observation. It leaves room for doubt. It leaves room for debate. Another limitation lies in how satellite data is prioritized. Global systems are designed to monitor phenomena that affect large populations: hurricanes, climate trends, sea level rise. A localized hazard in a remote stretch of ocean does not always justify dedicated coverage. Resources are finite. Observation time is allocated strategically. The Devil's Sea falls between priorities. It is too localized to dominate global models, too dangerous to ignore entirely, and too complex to monitor easily. This places it in a category that science handles less comfortably, not because it is unsolvable, but because it resists efficiency. There is also a temporal mismatch. Satellites are excellent at capturing gradual change. The Devil's Sea produces abrupt events. The tools lag behind the behaviour. Even high-resolution satellite systems struggle with the vertical dimension. They see the ocean as a surface. But the most important processes in this region occur beneath it. Heat rises from below, gas ascends through the water column. Pressure shifts propagate upward. None of these are easily visible from space. This vertical blindness is not a flaw so much as a constraint. Satellites were never meant to replace in situ observation, they were meant to complement it. In regions where in situ observation is sparse or risky, that complement becomes incomplete. The loss of the research vessel highlighted this limitation painfully. A ship sent to observe subsurface activity vanished, taking its instruments with it. Satellites could confirm only that the ship stopped transmitting. They could not say why. This moment underscored a fundamental truth. No matter how advanced our technology becomes, some environments still require presence, and presence carries risk. In response, scientists have pursued hybrid approaches. Autonomous underwater vehicles gather data without crews. Seafloor observatories monitor seismic and chemical activity continuously. These systems feed data upward, filling some of the gaps satellites leave behind. But even these systems have limits. Autonomous vehicles have finite battery life. Seafloor sensors are fixed in place and vulnerable to the very instability they are meant to observe. Data transmission can fail. Coverage remains partial. The Devil's Sea exploits these partialities. Its hazards are not constant enough to be predictable, nor frequent enough to be easily sampled. They exist in a narrow band of time and space where observation is least likely. This creates a psychological effect as well. When technology fails to provide clarity, humans tend to fill the gap with narrative. Mystery grows not because evidence is absent, but because it is incomplete. The Devil's Sea becomes unsettling not because nothing is known, but because what is known never feels sufficient. Scientists are keenly aware of this dynamic. They resist sensationalism. They emphasize uncertainty. They speak in probabilities rather than absolutes. To the public, this can sound evasive. In reality, it reflects intellectual honesty. Saying, "we don't know yet," is not a failure. It is an acknowledgement of scale, complexity, and limitation. Satellites have transformed our understanding of the ocean. Without them, many of the processes shaping the Devil's Sea would remain entirely invisible. We would know less, not more. But they have also revealed how much remains beyond reach. They show us patterns, not moments, averages, not extremes, surfaces, not depths. The Devil's Sea operates in moments, extremes, and depths. This mismatch ensures that the region will continue to challenge explanation, not because it defies physics, but because it occupies the narrow spaces where observation struggles most. As monitoring technology improves, some of these gaps will shrink. Resolution will increase. Coverage will expand. Models will become more sophisticated, but there will likely always be events that slip through. And when they do, the sea will return to calm, satellites will record nothing unusual, and scientists will be left reconstructing what might have happened based on fragments. This is not unique to the Devil's Sea, but it is concentrated there. It is a reminder that global vision does not equal local certainty, that seeing everything does not mean understanding everything. As long as hazards arise from below, unfold quickly, and leave minimal trace, satellites will struggle to explain them fully. They will hint, they will contextualize, they will narrow possibilities, they will not provide closure, and that lingering lack of closure is part of what keeps scientists uneasy, not because the Devil's Sea is unknowable, but because it exposes the edge of what our most powerful tools can reliably observe. Science is often imagined as a steady march towards certainty, a process where questions are asked, experiments are run, data is collected, and answers emerge cleanly on the other side. In many fields, this picture is mostly accurate. Variables can be isolated, conditions controlled, results repeated. Over time, uncertainty shrinks, confidence grows, the unknown recedes. The Devil's Sea does not cooperate with that narrative. Here, science does not move in straight lines. It circles. It revisits the same questions with better tools and still finds gaps. It replaces old explanations with more detailed ones. only to discover that the details introduce new uncertainties. The unknown does not retreat so much as change shape. This is not a failure of science, it is a confrontation with its limits. The scientific method depends on observation, measurement, and repeatability. In controlled environments, these are achievable. In deep, unstable, ocean regions shaped by tectonic activity, they are aspirational. The Devil's Sea is not a laboratory. It is an active system that does not pause for study. Events happen when they happen. Evidence appears briefly, if at all. Repeating conditions precisely is impossible. Scientists studying this region are not trying to solve it in the way one might solve a puzzle. They are trying to reduce uncertainty where possible and acknowledge it where it persists. This distinction is important because it shapes expectations. The public often wants definitive answers, clear causes, firm conclusions. Science, when practiced honestly in environments like this, rarely delivers those. Instead, it offers probability. One of the central tensions in studying the Devil's Sea is that none of the proposed mechanisms are extraordinary on their own. Submarine volcanoes exist elsewhere. Methane hydrates are found across the ocean floor. Rogue waves occur in many parts of the Pacific Ocean. Magnetic anomalies are well documented in volcanic regions. What makes this area unsettling is not novelty but convergence. Science excels at isolating variables. It struggles when variables interact in nonlinear ways. In the Devil's Sea, hazards do not queue politely. They overlap. A small seismic event may destabilize sediment. That sediment shift may release gas. Gas release may alter buoyancy. Altered buoyancy may compromise stability. Magnetic interference may delay corrective action. A rogue wave may strike at the worst possible moment. None of these steps is guaranteed. Together they form a chain where failure becomes possible, even when each link alone is unlikely. Modelling such chains is difficult. Each step introduces uncertainty. Small errors propagate. Outcomes branch. Scientists can describe plausible pathways without being able to say which one occurred in a specific incident. This is deeply unsatisfying to those accustomed to clear attribution. Another challenge lies in data scarcity. The most catastrophic events destroy their own evidence. Ships sink, instruments are lost, sensors go silent. What remains are indirect traces, if any. This biases the data set toward survivable incidents. Near misses are overrepresented. Total losses are underrepresented. This skew complicates statistical analysis. Researchers are acutely aware of this bias. They attempt to compensate by combining sources, historical records, survivor accounts, geological surveys, chemical measurements, satellite data. Each adds context. None fills the gaps entirely. This creates a situation where science can say what is possible, what is likely, and what is less likely, but rarely what is certain. The phrase science versus the unknown suggests conflict. In reality, the relationship is more nuanced. Science does not fight the unknown. It maps it. It defines its boundaries. It identifies where knowledge ends and why. In doing so, it often reveals that the unknown is not a single void, but a patchwork of partially understood processes. In the Devil's Sea, the unknown is not an absence of explanation. It is an excess of interacting explanations. This abundance creates its own discomfort. When multiple mechanisms can plausibly account for an outcome, choosing one feels arbitrary. Scientists resist that impulse. They prefer to hold multiple hypotheses in tension, updating confidence as new data arrives. This restraint is a strength, but it can be mistaken for indecision. Public discourse often struggles with this posture. Media narratives prefer resolution. Mysteries demand endings. When science refuses to provide them, frustration fills the gap. Speculation rushes in. Simplified stories gain traction. Scientists working on the Devil's Sea are aware of this dynamic. Many choose their words carefully. emphasizing what is known without overstating conclusions. They speak about risk rather than certainty, about environments rather than causes, about systems rather than events. This approach does not eliminate fear, it reframes it. Instead of asking why a specific ship vanished, researchers ask how likely it is for ships to encounter conditions that exceed their design limits in this region. Instead of seeking a single explanation, they assess cumulative risk. This shift moves the conversation from mystery to management. Yet even risk management has limits. Risk models rely on historical data. They assume that future conditions will resemble past ones within some margin. In a dynamic geological environment, that assumption weakens. Volcanic activity changes the seafloor. Climate change alters ocean temperatures and currents. Human activity increases traffic density. The baseline shifts. Science can update models, but it cannot freeze the system long enough to test them conclusively. This reality forces a kind of intellectual humility that is not always comfortable. It means admitting that some environments cannot be fully tamed by knowledge alone, that safety improvements reduce risk but do not eliminate it. That understanding grows asymptotically, approaching completeness without reaching it. The Devil's Sea exposes this truth starkly. For scientists trained to value control and prediction, this exposure is challenging. It pushes them toward interdisciplinary thinking. Geology alone is insufficient. Oceanography alone is insufficient. Engineering alone is insufficient. Understanding emerges only when these fields interact, and even then gaps remain. This interdisciplinary approach has led to meaningful progress. Better seafloor maps, improved understanding of gas hydrate dynamics, enhanced awareness of rogue wave formation, more conservative navigation practices, fewer losses. But progress does not equal closure. There remains a residue of uncertainty that science acknowledges but cannot erase. This residue is not mystical, it is structural. It arises from the scale, complexity, and inaccessibility of the system under study. Some scientists argue that this residue will shrink over time, that as technology improves, observation will become more continuous, that autonomous systems will fill gaps, that machine learning will detect patterns humans miss. These are reasonable expectations. Others are more cautious. They point out that new tools often reveal new layers of complexity. That increased resolution does not always simplify interpretation. That systems can remain unpredictable even when well observed. Both perspectives coexist. This coexistence reflects a broader philosophical tension within science itself. Is the goal to eliminate uncertainty, or to understand how to live with it? In fields like particle physics or chemistry, elimination feels achievable. In fields like climate science, ecology, and deep oceanography, management becomes the more realistic aim. The Devil's Sea aligns more closely with the latter. This does not diminish the value of scientific inquiry. On the contrary, it highlights its role as a guide rather than a guarantee. Science informs decisions. It shapes behaviour. It reduces blind spots. It does not promise invulnerability. Understanding this distinction is crucial for how society responds to places like the Devil's Sea. Expecting science to deliver certainty sets it up for perceived failure. Accepting that some uncertainty is irreducible allows for more nuanced policy and practice. Mariners who operate in the region do not demand absolute safety. They demand informed caution. Scientists provide that by outlining risks, even when they cannot specify exact triggers. Governments translate that into guidelines. Insurance models adjust. Routes shift. Behaviour adapts. This is science at work, not as a solver of mysteries, but as a manager of complexity. The unknown in this context is not an enemy. It is a condition, one that requires respect rather than conquest. One that reminds us that the planet operates on scales and timescales larger than human planning. The Devil's Sea sits at the intersection of this realization. It is a place where science has illuminated much and still leaves shadows, where explanations exist without certainty, where progress does not erase unease, and perhaps that is the most honest outcome science can offer here. Not reassurance, but clarity about limits. Not closure, but context. As long as those limits remain, the Devil's Sea will continue to unsettle, not because it is inexplicable, but because it exemplifies the edge of human understanding. A place where knowledge advances and humility must advance with it. And it is precisely at that edge, where science meets the unknown without pretending to defeat it, that the story continues. When clear answers fail to arrive, something else almost always takes their place. Not immediately, and not always loudly, but steadily, filling the space left behind by uncertainty. Humans are not comfortable with gaps. We are pattern-seeking by nature, and when explanation stops short, imagination keeps going. This is not a flaw in thinking. It is a survival trait. It is also why myth tends to grow strongest in places where evidence thins out. The Devil's Sea is one of those places. It is important to understand that myth does not emerge because people are foolish or uninformed. Myth emerges because lived experience demands meaning, even when formal explanation lags behind. When ships disappear without wreckage, when instruments fail without obvious cause, when official reports end with cautious language and unresolved conclusions, people do not simply accept the silence. They narrate it. In coastal communities, those narratives took shape long before scientists arrived with instruments and charts. Fishermen needed ways to communicate danger that went beyond statistics. Telling someone that a region has a higher probability of unpredictable subsurface gas release is not useful if the listener lacks the framework to understand it. Telling them that a dragon sleeps beneath the water and does not like to be disturbed accomplishes something similar in far fewer words. The myth is not the explanation, it is the warning. In Japanese maritime folklore, the sea has never been treated as an empty backdrop. It is animated, reactive, and capable of intention in a symbolic sense. Sea spirits, dragons, and demons are not portrayed as random agents of chaos. They are often tied to specific locations and behaviours. They punish arrogance, they respond to disrespect, they act when boundaries are crossed. These stories encode rules. Do not linger where you're not welcome. Do not assume calm equals safety. Do not treat the sea as something you control. Long before geology could describe subduction zones or oceanography, could model rogue waves, myth carried those lessons forward. It ensured that caution survived across generations even when the reasons behind it could not be articulated technically. As outside observers began labelling the Devil's Sea as mysterious or cursed, a misunderstanding emerged. Myth was interpreted as belief rather than practice, as though fishermen truly thought monsters dragged ships under. In reality, the myth functioned more like a shared language for risk. Science, by contrast, prefers specificity. It seeks mechanisms. It separates metaphor from measurement. This difference in approach can create friction. When scientists dismiss myth entirely, they risk overlooking the behavioural wisdom embedded within it. When myth dismisses science, it risks freezing caution into superstition. In the Devil's Sea, these two modes of understanding coexist uneasily. Modern researchers do not invoke demons or dragons. They talk about volcanic arcs, methane hydrates, and non-linear wave dynamics. And yet, the lived outcome described by both perspectives is remarkably similar. This is a place where the sea does not give second chances. A place where danger arrives without warning. A place where absence follows quickly and quietly. When science cannot yet connect all the dots, myth provides continuity. It preserves memory. It keeps attention focused on specific locations long after individual incidents fade from record. In this way, myth functions as a cultural archive, maintaining awareness across centuries where formal documentation is sparse. This is why myth thrives not only in the past but in the present. Even today, with satellites and sensors and models, the Devil's Sea resists closure. Scientists offer plausible explanations but rarely definitive ones. They speak in probabilities and interactions. They acknowledge limits. That honesty, while necessary, leaves room for alternative narratives to persist. The human mind does not like probabilistic danger. It prefers stories with agents, intentions, and boundaries. Myth supplies those elements. It turns diffuse risk into something graspable. Importantly, myth does not always contradict science. Sometimes it runs parallel to it, describing the same reality from a different angle. Where science says, this region exhibits overlapping geological and oceanographic hazards, myth says, this place is dangerous and should be treated with respect. The instruction is the same. Problems arise when myth is mistaken for literal explanation, or when science is expected to eliminate uncertainty entirely. Neither is equipped to do the other's job. The persistence of myth around the Devil's Sea also reflects how people respond to unresolved loss. When a ship disappears and no cause is confirmed, grief seeks narrative. Families want to know why. Communities want to remember. Myth offers a way to hold that loss without pretending it makes sense. A demon or dragon does not need to be real to serve this function. It provides a shape for grief, a name for absence, a reason that, while not factual, feels less empty than silence. This does not mean myth is harmless in all forms. Sensationalized versions can distort understanding, attract unnecessary fear, or overshadow real safety concerns. But at its core, myth arises from the same place as science, a desire to understand, to predict, to avoid repeating harm. Where science advances slowly due to complexity, myth advances quickly through narrative. Where science hesitates to conclude, myth does not. This asymmetry explains why myths often outpace explanations in environments like the Devil's Sea. It is not that science is failing, it is that the system under study resists compression into simple cause and effect stories, and so, myth fills the compression gap. Over time, some myths fade as explanations solidify. Others persist because explanations remain partial. The Devil's Sea belongs to the latter category. Each scientific advance narrows the unknown without erasing it. Each model explains some losses while leaving others ambiguous. As long as ambiguity remains, myth will remain too. This is not a competition between rationality and imagination. It is a reflection of how humans adapt to uncertainty. Science manages risk through analysis and caution. Myth manages it through memory and meaning. Both influence behavior, both shape decisions. The most dangerous assumption would be that myth thrives only because people lack knowledge. In reality, myth often thrives because knowledge is incomplete. The Devil's Sea demonstrates this clearly. Despite decades of research, advanced technology and careful study, it still cannot be fully explained in a way that satisfies every question. That gap is not large, but it is persistent, and into that narrow space stories continue to flow. Not because people want to believe in monsters, but because they want to remember where danger lives. As long as ships pass over unstable seabeds, as long as the sea behaves unpredictably, as long as some losses leave no evidence behind, myth will remain a companion to science rather than its enemy. And perhaps that is not a weakness, but a reminder that even in an age of data and detection, some places demand more than explanation. They demand respect, restraint, and the humility to accept that not every warning arrives in the language we prefer. The Devil's Sea does not need myth to be dangerous, but myth ensures that its danger is not forgotten while science continues the slower work of understanding why. There is a temptation, when discussing places like the Devil's Sea, to frame them as problems of the past, to imply that whatever danger once existed has been tamed by better ships, better data, and better judgment. The number of disappearances has declined. Routes are better understood. Technology has advanced. From a distance, it can look as though the story is winding down. Up close, that confidence begins to feel premature. The Devil's Sea has not gone quiet. It has simply become more selective about how it reminds us of its presence. Modern ships cross the region, with greater awareness and caution than their predecessors, but the underlying forces that shaped its reputation have not stopped operating. The seabed has not stabilised. Volcanic systems have not shut down. Geological stress continues to build and release itself beneath the surface of the Western Pacific Ocean. What has changed is how often humans place themselves in the most vulnerable positions. Shipping routes have been adjusted subtly over time. Areas once traversed routinely are now approached more conservatively. Research missions plan carefully, minimizing exposure and increasing redundancy. Fishing fleets guided by both experience and regulation avoid lingering in zones known for instability. These adaptations reduce risk, but they do not eliminate it. They simply acknowledge it. The sea, however, does not adapt to us. Submarine volcanic activity continues on its own schedule. Some eruptions are detected. Others are inferred only after the fact. Seismic networks capture tremors, but not all movement produces clear signals. Heat flows upwards slowly, altering water temperature gradients in ways that are difficult to predict. Gas continues to accumulate in sediments, occasionally released by subtle shifts that escape notice. These processes do not announce milestones. They do not pause because fewer ships pass overhead. They do not care whether a vessel is commercial, scientific, or recreational. They operate continuously, shaped by forces far older than navigation. From a scientific standpoint, this continuity is unsettling. It means that the absence of recent disasters cannot be taken as proof of safety. It means that risk is dynamic rather than static. Conditions today are not identical to conditions 10 years ago, even if surface behaviour appears similar. Climate change adds another layer of uncertainty. Ocean temperatures are rising, albeit unevenly. Warmer water affects density, current behaviour, and chemical stability. Over long timescales, it may influence the stability of methane hydrates trapped beneath the seabed. Small changes in temperature can have outsized effects when systems are already near critical thresholds. Scientists studying hydrate stability are cautious in their conclusions. They avoid alarmism. The processes involved unfold over decades or centuries, not overnight. But caution does not mean dismissal. It means acknowledging that the baseline is shifting, even if the consequences are not immediate. In regions like the Devil's Sea, where multiple hazards already overlap, even small shifts matter. There have been recent incidents that, while not as dramatic as earlier losses, serve as reminders. Reports of unexpected sea behaviour, instruments requiring recalibration more frequently than anticipated, sudden current changes that complicate manoeuvring. These events rarely make headlines. They're absorbed into routine operations, noted and adjusted for. But they indicate that the environment remains active. One of the challenges in assessing whether the sea is finished lies in how success is measured. Fewer ship losses are rightly seen as progress, but progress in safety does not necessarily reflect a reduction in hazard. It often reflects improved avoidance. The danger remains, exposure decreases. This distinction is subtle, but critical. It affects how future risk is perceived. If safety improvements are mistaken for environmental stabilisation, complacency can creep in. That complacency erodes margins. Researchers emphasise that the Devil's Sea is not a single hazard zone that can be mapped once and avoided forever. Its risks are distributed and shifting. New volcanic features form, old ones collapse, sediment layers migrate, gas pockets evolve. What was safe last year may be less so next year. Continuous monitoring is the ideal response. In practice, it is constrained by cost, logistics, and technology. Deep-sea observatories provide valuable data, but coverage is limited. Autonomous systems help, but they cannot be everywhere at once. Satellites offer context, not detail. This leaves a persistent gap between what is known and what is happening at any given moment. For mariners, this gap is navigated through conservatism, extra margins, redundant systems, contingency planning. These measures reduce vulnerability, but they also slow operations and increase costs. There is always pressure to optimize, to shave time and expense. In regions like the Devil's Sea, that pressure must be resisted. The sea is unforgiving of optimization that ignores uncertainty. There is also a generational aspect to how risk is perceived. Those who experienced or studied earlier losses carry institutional memory. They remember why certain practices were adopted. As time passes without major incidents, that memory fades. New personnel may view restrictions as overly cautious. They may trust technology more than tradition. This cycle is not unique to maritime operations. It appears in aviation, engineering, and medicine. Safety measures born from hard lessons are questioned once those lessons are no longer lived experience. The Devil's Sea tests whether those lessons will be remembered long enough to remain effective. Government agencies remain aware of this risk. Official advisories may not change dramatically, but internal assessments continue. Data is reviewed, models updated, research funding allocated carefully. The goal is not to eliminate danger, but to stay ahead of it. International collaboration has increased. Oceanographic data is shared. Geological surveys inform broader models of tectonic behaviour. The Devil's Sea is studied not in isolation, but as part of a larger system that includes other active regions of the Pacific. This broader perspective reveals something important. The Devil's Sea is not unique in being dangerous. It is distinctive in how multiple dangers overlap in a relatively compact area, near heavily trafficked routes. That combination amplifies consequences. The sea's continued relevance is also psychological. It occupies a place in maritime culture as a reminder that progress has limits, that even as tools improve, the environment can still surprise. This awareness shapes behaviour in subtle ways. It encourages caution where confidence might otherwise dominate. Scientists too feel this influence. The region remains a case study in humility. It resists definitive classification. Each proposed explanation illuminates one aspect while leaving others untouched. The picture sharpens without becoming complete. This incompleteness does not mean that science is losing ground. It means that the ground is uneven. The Devil's Sea continues to generate questions precisely because it sits at the edge of predictability. It is not chaotic in a random sense. Its behaviour follows physical laws. But those laws interact in ways that are difficult to observe and model comprehensively. As long as that remains true, the sea is not finished with us. It will continue to demand attention from researchers refining models of submarine volcanism and gas dynamics. It will continue to influence navigation practices. It will continue to serve as a reminder that absence of disaster is not the same as absence of risk. The next incident, if it occurs, may not resemble the last. It may be smaller, it may be less visible, it may be recorded as an anomaly rather than a mystery, or it may slip through observation entirely, leaving behind only questions and adjustments quietly made. That possibility lingers. The Devil's Sea does not operate on human timelines. It does not escalate neatly toward a climax. It does not conclude. It persists, shaped by forces that predate our presence and will outlast it. Understanding this persistence is crucial. It shifts the narrative away from resolution and toward coexistence. Humans will continue to cross these waters. Science will continue to study them. Technology will continue to improve. The sea will continue to be what it is. That balance, uneasy and unfinished, defines the relationship. Not a battle to be won, and not a mystery to be solved once and for all, but an ongoing negotiation between human ambition and planetary process. And as long as that negotiation continues, the Devil's Sea remains part of the present, not a relic of the past. There is an expectation woven quietly into modern life that everything important can eventually be explained. That with enough data, enough processing power, enough patience, uncertainty will give way to clarity. This expectation is rarely stated outright, but it shapes how we talk about science, safety, and progress. When something resists explanation, the discomfort it creates often feels disproportionate to the scale of the event itself. The Devil's Sea unsettles scientists not because it is violent all the time, but because it refuses to fully satisfy that expectation. We live on a planet where oceans cover most of the surface, and yet we interact with them as if they should conform to our needs. We expect shipping lanes to be reliable, we expect navigation systems to be authoritative, we expect that when something goes wrong, there will be a cause we can isolate, name and correct. These expectations are understandable, they are also incomplete. The ocean does not operate as a service. It is not obligated to make its processes legible to us. It does not escalate gradually because that would be fair. It does not leave evidence because evidence is useful. It does not pause so we can measure, observe, or interpret. It does not care whether the tools we rely on are sufficient to capture what it's doing at any given moment. The Devil's Sea makes this indifference harder to ignore. Over the course of this exploration, patterns have emerged. Not neat ones, not conclusive ones, but persistent ones. Ships vanishing without wreckage, instruments behaving inconsistently, sudden hazards appearing without warning, geological activity reshaping the seafloor continuously, gas releases altering buoyancy invisibly, waves forming where theory says they should not, satellites watching from above and missing the most critical moments. None of these phenomena are supernatural. Every one of them fits within known physical laws, and yet, taken together, they produce outcomes that feel deeply unsatisfying to human expectations. The explanations exist, but they do not close the case. They reduce mystery without eliminating it. This is the point where frustration often sets in. Why can't science just tell us exactly what happened? Why can't we pin down a single cause? Why does every answer seem provisional? The uncomfortable truth is that clarity is not guaranteed, even in principle. Some systems are too complex, too dynamic, too poorly observed to yield definitive reconstructions. The Devil's Sea is one of those systems. Events unfold across vertical layers of water, over unstable geology, influenced by processes that may never be measured directly. When something goes wrong, the conditions that caused it may no longer exist by the time anyone looks. This is not a temporary limitation awaiting the next technological breakthrough, it is a structural feature of the environment. Science is often described as a tool for conquering uncertainty. In reality, its more honest role is to describe uncertainty accurately, to tell us where confidence is justified and where it is not, to replace false certainty with informed caution. The Devil's Sea demands that kind of honesty. It exposes the difference between knowing how something can happen and knowing that it did happen. Scientists can describe multiple plausible pathways that could lead to a ship's disappearance. They can rank those pathways by likelihood. They can rule out some causes, but they cannot always collapse possibility into certainty. That gap is not a failure of method. It is a reflection of reality. The ocean, particularly in regions shaped by tectonic instability, is not a static system waiting to be decoded. It is a constantly evolving interface between heat, pressure, chemistry, and motion. The surface we see is only the thinnest expression of processes unfolding kilometers below. When we ask the ocean for clarity, we're asking it to slow down, simplify, and preserve evidence for our benefit. It has no incentive to do so. This realization forces a recalibration of how we think about risk. Safety at sea has never meant eliminating danger. It has meant managing it, anticipating what can be anticipated, leaving margins for what cannot. The Devil's Sea sits at the boundary of those two categories. Much has been learned. Routes are planned with greater care. Certain zones are avoided. Research is conducted with redundancy and restraint. Losses have decreased. These are real achievements. They reflect the power of accumulated knowledge and collective memory, but they do not imply mastery. The ocean remains capable of producing events that fall outside prediction. It remains capable of surprising even the best prepared systems. It remains capable of acting in ways that are consistent with physics and still deeply unsettling to experience. This is why scientists continue to approach the Devil's Sea with caution rather than confidence. Not because they believe it is unknowable, but because they understand that knowledge here will always be incomplete. There is a humility embedded in that stance that is easy to overlook. Modern culture often celebrates certainty. Experts are expected to provide answers, not ranges, to speak definitively, not conditionally, to reassure rather than complicate. In environments like the Devil's Sea, those expectations are not just unrealistic, they are dangerous. False certainty invites complacency. The history of maritime loss is filled with examples of overconfidence, ships declared unsinkable, routes deemed safe, technologies assumed infallible. Each failure teaches the same lesson in different language. The ocean does not respect our assurances. In this sense, the Devil's Sea is not uniquely hostile. It is unusually honest. It strips away illusions of control more efficiently than most places. It forces those who study it to confront the limits of prediction directly. It reveals where our models are strongest and where they falter. This confrontation has value beyond one region. What scientists learn here informs how other complex environments are approached. It shapes thinking about cascading risk, about systems failure, about the interaction between natural processes and human design. It encourages interdisciplinary work and cautious interpretation. It also reshapes how absence is understood. When a ship disappears without trace, the instinct is to treat that absence as a problem to be solved. Sometimes it is. Other times it is simply a consequence of scale. The ocean is vast. The seafloor is deep. Processors erase evidence quickly. Expecting complete reconstruction in every case may be unreasonable. This does not mean giving up. It means adjusting expectations. Clarity is not a right. It is a privilege granted by certain conditions: stable environments, reproducible processes, accessible evidence. When those conditions do not exist, science adapts by shifting its goals. Instead of asking for full explanations, it asks better questions. Instead of seeking certainty, it seeks reduction of risk. Instead of promising control, it offers guidance. The Devil's Sea fits this reframed relationship. It is a place where science informs behaviour without closing the narrative, where understanding grows without resolving every doubt, where progress is measured not by elimination of mystery, but by fewer losses and better decisions. This reframing is uncomfortable because it resists closure. There is no final answer that ties everything together neatly, no single cause to point to, no definitive explanation that silences further inquiry. But discomfort is not the same as failure. In fact, discomfort can be a signal that expectations are being recalibrated appropriately, that we are learning to coexist with uncertainty rather than denying it. The ocean does not owe us clarity any more than it owes us calm seas or favourable winds. It does not operate on our terms. It does not guarantee transparency. It does not preserve evidence out of fairness. What it does offer, consistently, is feedback. When routes are chosen poorly, it pushes back. When assumptions are too rigid, it exposes them. When margins are too thin, it narrows them further. This feedback is not moral, it is mechanical. It follows physical laws without regard for human intention. The Devil's Sea has delivered that feedback repeatedly over time. Each disappearance, each instrument anomaly, each unexplained event has nudged behaviour in small ways, adjusted routes, revised models, more cautious planning. The absence of catastrophe in recent years is not proof that the sea has changed. It is evidence that humans have learned to listen more carefully. Listening in this context does not mean believing in myth or surrendering to fear. It means accepting that some environments demand humility. that some risks cannot be eliminated, only respected. The Pacific Ocean is vast, complex and active. The Devil's Sea is one expression of that reality, not an exception to it. It reminds us that even with global monitoring, advanced modelling, and centuries of accumulated experience, there are still places where the margin between routine and disaster is thinner than we would like. That thinness is not a flaw in nature, it is a condition of operating within it. The desire for clarity is deeply human. It drives exploration, science and innovation. Without it, progress would stall. But clarity cannot be demanded from systems that are not obligated to provide it. The ocean teaches this lesson repeatedly, often quietly, sometimes harshly. The Devil's Sea teaches it particularly well, not through spectacle, not through constant danger, but through selective reminders, through moments where confidence dissolves, through questions that remain open, through the realization that understanding can grow without ever becoming complete. And perhaps that is the most enduring takeaway. Not that the sea is hostile or mysterious or malevolent, but that it is indifferent to our need for narrative closure, indifferent to our preference for certainty, indifferent to whether we are watching closely enough to see what it is doing beneath the surface. The ocean does not owe us clarity. What it offers instead is a relationship, one that requires patience, caution, and respect, one that rewards humility more than confidence, one that continues whether or not we feel satisfied by our explanations. As long as humans cross these waters, study them, and rely on them, that relationship will persist. Not as a problem to be solved, but as a condition to be navigated. And in that ongoing navigation, the Devil's Sea remains what it has always been. Not a riddle demanding an answer, but a reminder that some parts of the world will always exist just beyond the reach of complete understanding, asking us not for certainty, but for care.